Right now, 3I/Atlas, the second confirmed interstellar comet, continues its impossible journey through our solar system. You've heard the name before, but what makes it truly staggering is what it represents. A time capsule older than our sun, carrying chemistry and physics from a part of the galaxy we've never sampled directly. This isn't just another icy rock drifting past. It's a messenger from billions of years and light years away, rewriting what astronomers thought was possible. Before we get into the 49 mind-bending facts that make Atlas one of the strangest visitors we've ever encountered, smash that like button to help more people discover this story. Hit subscribe and ring the notification bell so you don't miss our future deep dives into the universe's greatest mysteries. And try out YouTube's new hype feature right below this video. It's a powerful way to support creators. Finally, if you've got your own favorite science fact that's so wild it blows your mind, drop it in the comments. You might see it featured in a future video. Now, let's dive into the extraordinary story of 3I/Atlas and explore how this interstellar wanderer is challenging everything we thought we knew about the cosmos. Fact 1. The third cosmic messenger. 3I/Atlas is officially the third confirmed interstellar object ever discovered visiting our solar system. Think about that for a moment. In all of human history, with all our telescopes and space missions, we've only confirmed 3 objects that originated from beyond our solar system. The first was the mysterious Oumuamua in 2017, which sparked debates about alien technology. The second was 2I/Borisov in 2019, which behaved more like a traditional comet. But 3I/Atlas, it's in a category all its own, challenging everything we thought we knew about interstellar visitors. To understand how extraordinary this discovery is, we need to appreciate the rarity of these encounters. Our solar system is like a tiny island in an ocean of space that's roughly 100,000 light-years across. The chances of an interstellar object randomly wandering into our cosmic neighborhood are astronomically small. Yet, here we are, witnessing our third such visitor in less than a decade. This suggests that the designation 3I follows the International Astronomical Union's naming convention established after the discovery of Oumuamua. The I stands for interstellar, distinguishing these objects from comets and asteroids that originated within our solar system. The number indicates the order of discovery, making 3I/Atlas a historic milestone in our exploration of interstellar visitors. What makes 3I/Atlas particularly significant is that unlike its predecessors, it was discovered well before reaching its closest approach to the Sun. Oumuamua was spotted as it was already leaving our solar system, giving astronomers only a brief window to study it. 2I/Borisov provided more observation time but was relatively small and faint. 3I/Atlas, however, offers an unprecedented opportunity for detailed study throughout its entire passage through the inner solar system. The statistical implications of discovering 3 interstellar objects in such a short time frame are staggering. If these discoveries represent a typical rate of interstellar visitors, it suggests that our solar system receives roughly one such visitor every 3 to 4 years. This would mean that over the 4.6 billion year history of our solar system, millions of interstellar objects may have passed through our cosmic neighborhood, each carrying information about distant star systems and ancient galactic conditions. Fact 2. A discovery that almost didn't happen. On July 1st, 2025, the Atlas telescope system in Rio Hurtado, Chile, detected system wasn't specifically looking for interstellar objects. It was designed to find potentially dangerous asteroids that might threaten Earth, but sometimes the universe has other plans. The astronomers who first spotted it had no idea they were looking at something that had been traveling through space since before our solar system even existed. The Atlas system consists of 4 telescopes strategically positioned around the globe, 2 in Hawaii, 1 in Chile, and 1 in South Africa. These robotic sentinels automatically scan the entire visible sky multiple times each night, comparing images to detect moving objects. The system processes thousands of images nightly, using sophisticated algorithms to identify potential threats to Earth. On that fateful July evening, the Chilean telescope's cameras captured 4 images of what initially appeared to be just another faint moving object against the star field. What made this detection particularly challenging was 3 I/Atlas's apparent magnitude of 17.8, incredibly faint by astronomical standards. At this brightness level, the object was roughly 1,000 times dimmer than the faintest stars visible to the naked eye. Only the most sensitive telescopes equipped with advanced CCD cameras could detect such a dim object against the cosmic background. The fact that Atlas managed to spot it at all is a testament to the system's remarkable sensitivity and the dedication of the astronomers who built and operated. Larry Deneau, a member of the Atlas team at the University of Hawaii, was among the first to recognize the significance of the discovery. However, as he later noted, the team had experienced false alarms before with interesting objects that initially appeared unusual, but turned out to be conventional solar system bodies. It wasn't until additional observations confirmed the object's hyperbolic trajectory that the team realized they had discovered something truly extraordinary. The discovery process involved a complex series of follow-up observations and calculations. Within hours of the initial detection, astronomers around the world were alerted through the Minor Planet Center, the international clearinghouse for asteroid and comet discoveries. Telescopes in multiple countries began tracking the object, gathering the positional data necessary to calculate its precise orbit. It was this orbital analysis that revealed the object's interstellar origin, confirming that it was moving too fast to be gravitationally bound to the Sun. Particularly fortuitous. Had 3 I/Atlas been spotted just a few weeks later, it would have been much closer to the Sun and significantly more difficult to observe due to solar glare. Had it been discovered earlier while still farther out in the solar system, it might have been too faint for detailed follow-up observations with smaller telescopes. The July discovery provided the optimal balance of brightness and observability that has made the extensive study of this object possible. Fact 3. The fastest thing we've ever seen. 3 I/Atlas is moving through our solar system at an absolutely staggering 130,000 miles per hour. To put that in perspective, if you could travel that fast, you could circle the entire Earth in just over 11 minutes. This incredible speed isn't just impressive, it's proof of the object's interstellar origin. Nothing that formed in our solar system could naturally achieve such velocity. This speed tells us that 3 I/Atlas has been accelerated by countless gravitational encounters with stars and stellar nurseries during its billions of years wandering through the galaxy. The physics behind this extraordinary velocity tells a fascinating story of galactic wandering. When 3 I/Atlas first formed around its parent star billions of years ago, it likely had a relatively modest velocity, probably similar to the orbital speeds we see in our own solar system, perhaps a few dozen kilometers per second at most. However, something dramatic happened that ejected it from its birth system and set it on a journey through interstellar space. The ejection process itself could have involved several mechanisms. The most likely scenario involves a close encounter with a massive planet, similar to Jupiter, that provided enough gravitational energy to exceed the star's escape velocity. Alternatively, the object might have been expelled during the chaotic final stages of its parent star's evolution, or even through interactions with other stellar systems in a dense star cluster. Regardless of the initial ejection mechanism, once 3 I/Atlas entered interstellar space, its journey was just beginning. Over billions of years of galactic wandering, 3I/Atlas encountered countless gravitational influences that gradually increased our stellar cluster or massive molecular cloud. It received a gravitational kick that added to its momentum. This process, known as gravitational scattering, works like a cosmic pinball machine, with each encounter potentially adding or subtracting energy from the object's motion. The current velocity of 130,000 miles per hour, approximately 58 kilometers per second, represents the accumulated result of billions of years of such encounters. To achieve this speed, 3I/Atlas likely passed through some of the most dynamically active regions of our galaxy, possibly including the vicinity of the galactic center, dense stellar clusters, or regions where massive stars were forming and dying in rapid succession. This velocity also has implications for the object's future trajectory. When 3I/Atlas eventually leaves our solar system, it will carry with it a slight gravitational influence from its encounter with the Sun and planets. However, this influence will be minimal compared to the object's enormous kinetic energy. It will continue its journey through interstellar space at nearly the same speed, potentially encountering other star systems over the coming millions and billions of years. The measurement of such extreme velocities requires extraordinary precision in astronomical observations. Astronomers must track the object's position against the background stars over time, accounting for the motion of Earth, the telescope's location, and various relativistic effects. The fact that we can measure velocities to this precision represents one of the remarkable achievements of modern astrometry. Fact 4. A size that defies logic. Here's where things get truly mind-bending. According to Hubble's Space Telescope observations, 3I/Atlas has a nucleus that could be anywhere from just over 1,000 feet across to an incredible 3.5 miles in diameter. But some estimates suggest it could be even larger, potentially up to 15 miles across. If the larger estimates are correct, this would make 3I/Atlas not just the largest interstellar object we've ever seen, but so large that it challenges our understanding of how such objects can exist and travel between star systems. Objects, unlike planets or nearby asteroids, which we can study for extended periods and sometimes even visit with spacecraft, interstellar visitors provide only brief observation windows. Moreover, as 3I/Atlas approaches the Sun, it develops an extensive coma of gas and dust that obscures the actual solid nucleus, making direct size measurements nearly impossible. The Hubble Space Telescope, with its exceptional resolution and stability, has provided the most accurate size estimates to date. By carefully analyzing the brightness and spatial distribution of light from 3I/Atlas, astronomers can place constraints on the size of the solid nucleus. However, even these measurements are complicated by the fact that we don't know the object's exact composition, surface properties, or rotation state, all factors that affect how it reflects sunlight. The size estimates have important implications for our understanding of interstellar object populations. If 3I/Atlas is indeed as large as some estimates suggest, it would be extremely massive, potentially containing millions or billions of tons of material. Such massive objects should be relatively rare in interstellar space, making their detection statistically unlikely. This has led some astronomers to propose that either our estimates of interstellar object populations are wrong, or that 3I/Atlas represents an unusually lucky discovery. Theoretical models of galactic evolution suggest that smaller interstellar objects should vastly outnumber larger ones, following what's known as a size-frequency distribution. If 3I/Atlas is truly massive, it would represent the rare large end of this distribution. However, the fact that we've detected such a large object among only 3 confirmed interstellar visitors might indicate that our detection methods are biased toward larger, brighter objects, and that countless smaller interstellar visitors pass through our solar system undetected. The size uncertainty also affects our understanding of the object's internal structure and composition. A larger object would likely have a more differentiated interior, with heavier materials settling toward the center and lighter, more volatile materials concentrated near the surface. This could explain some of the unusual outgassing patterns observed as 3I/Atlas approaches the Sun. Recent observations from the Vera C. Rubin Observatory have added another layer of complexity to the size question. Pre-discovery images show that 3I/Atlas's apparent size increased dramatically over a short period in late June and early July 2025, growing by approximately 3,700 miles in less than 2 weeks. This rapid expansion is consistent with the development of a large coma as the object became more active, but it also makes it more difficult to distinguish between the solid nucleus and the surrounding gas and dust envelope. Fact 5. The designation that tells a story. The name 3I/Atlas isn't random, every part has meaning. The C, 3 inches, indicates this is the third interstellar object we've discovered. The I stands for interstellar, marking it as a visitor from beyond our solar system. Atlas honors the telescope system that discovered it, but it also has another designation. C 2025 N1 Atlas, where the C indicates it's a comet. 2025 inches is the year of discovery, and N1 means it was the first comet discovered in the first half of July 2025. The dual naming system reflects the International Astronomical Union's attempt to create a coherent framework for classifying these rare interstellar visitors. When Oumuamua was first discovered in 2017, it initially received a standard asteroid designation before astronomers realized its interstellar origin. This led to the creation of the new I designation specifically for interstellar objects, with Oumuamua retroactively becoming 1I/Oumuamua. The comet designation C 2025 N1 follows traditional naming conventions that have been used for centuries. The C indicates a non-periodic comet, one that either has an orbital period longer than 200 years or, in this case, follows a hyperbolic trajectory and will never return. The year 2025 marks when it was discovered, while N represents the first half of July. Letters A through H cover January through April, I and J are skipped, and K through Y cover the rest of the year. The number 1 inch indicates it was the first comet discovered during that convention, carries forward a tradition that dates back to the earliest systematic observations of comets. Famous comets like Halley's Comet follow similar patterns, though they receive P designations to indicate their periodic nature. The fact that 3I/Atlas receives both an interstellar designation and a traditional comet name reflects its dual nature as both a comet and an interstellar visitor. The ATLAS acronym itself, Asteroid Terrestrial Impact Last Alert System, reflects the telescope's primary mission of detecting potentially hazardous asteroids that might threaten Earth. The fact that this Earth protection system discovered an interstellar visitor highlights the interconnected nature of astronomical research, where instruments designed for one purpose often make unexpected discoveries in completely different fields. The naming also honors the international collaboration that makes such discoveries possible. The ATLAS system, while funded by NASA, involves telescopes operated by the University of Hawaii's Institute for Astronomy and partners around the world. The discovery represents not just American achievement, but a global effort to monitor and understand our cosmic environment. Fact 6. Pre-discovery. Hidden in plain sight. Here's something that gives astronomers chills. 3I/Atlas was actually captured in images dating back to June 14, 2025, nearly 3 weeks before its official discovery. These pre-discovery observations were found in archives from multiple telescopes, including the Zwicky Transient Facility at Palomar Observatory in California. This means that for weeks, this ancient visitor from another star system was hiding in plain sight in our astronomical data, waiting to be recognized. The existence of pre-discovery images is both exciting and sobering for the astronomical community. It's exciting because it extends the observational baseline for 3I/Atlas, providing crucial additional data points for calculating its precise orbit and physical properties. However, it's also sobering because it highlights how much astronomical data we collect, but don't immediately analyze in detail. Modern astronomical surveys generate enormous amounts of data every night. The Zwicky Transient Facility alone captures hundreds of thousands of images annually, each containing millions of individual star measurements. The Catalina Sky Survey, Linear, NEOWISE, and other programs contribute additional massive datasets. Processing all this information in real time is beyond current computational capabilities, which means that many discoveries remain hidden in archives until triggered by specific events or searches. The pre-discovery observations of 3I/Atlas were identified through a process called precovery, retrospectively searching archived images for an object after its discovery, and orbital parameters are known. This detective work requires sophisticated software that can predict where an object should have appeared in past images, and then search those specific locations for faint moving sources. The June 14th observations are particularly valuable because they capture 3I/Atlas when it was still relatively far from the Sun and less active. This provides astronomers with a baseline for understanding how the object's behavior has changed as it approaches our star. The early images show a much more compact appearance, with little evidence of the extensive coma that became apparent in later observations. These pre-discovery observations also extend the arc of observation time, which is crucial for accurate orbit determination. The longer the time baseline over which an object is observed, the more precisely astronomers can calculate its trajectory, predict its future position, and understand its past motion through the solar system. In the case of 3I/Atlas, the additional weeks of observational data significantly improve our ability to predict its behavior as it continues its journey. The precovery process also revealed that 3I/Atlas appeared in images from multiple telescope systems, suggesting that it should have been detectable by several different surveys. This raises intriguing questions about automated detection algorithms and whether improvements in software could lead to earlier detection of future interstellar visitors. Fact 7. A chemical signature. Unlike anything we've seen, when the James Webb Space Telescope turned its powerful infrared vision toward 3I/Atlas, what it found was unprecedented. The comet has the highest carbon dioxide to water ratio ever recorded, an extraordinary 8:1. Most comets show the opposite pattern, with water typically dominating their composition. This bizarre chemistry suggests that 3I/Atlas formed in conditions completely unlike anything in our solar system, possibly near a carbon dioxide ice line around an ancient star. The implications of this chemical signature are profound and far-reaching. In our solar system, comets typically form in the outer regions where temperatures are low enough for water ice to condense and remain stable. The so-called snow line in our solar system occurs at roughly 3 to 5 astronomical units from the Sun, depending on the early solar system's temperature profile. Beyond this line, water ice can accumulate to form the nuclei of comets and the cores of gas giant planets. However, the extreme carbon dioxide dominance in 3I/Atlas suggests it formed in a very different environment. One possibility is that it originated near what astronomers call the CO2 ice line, of its parent star system, a region where temperatures were too warm for water ice to be stable, but still cold enough for carbon dioxide to condense. This would require specific temperature and pressure conditions that differ significantly from those in our own solar system's formation region. Another possibility is that 3 are a star with a different spectral type than our Sun. Different types of stars produce different amounts of heat and radiation at various wavelengths, which could create different condensation patterns in their surrounding protoplanetary disks. A cooler star might have its CO2 ice line closer in, while its water ice line might be farther out, creating conditions favorable for CO2-rich comet formation. The chemical composition also provides clues about the age and evolutionary history of 3 1/Atlas's parent system. In the early universe, successive generations of stars progressively enriched the interstellar medium with heavy elements through nuclear fusion and supernova explosions. A system with unusual CO2/H2O ratios might reflect formation from material with a different heavy element abundance than the material that formed our solar system. The detection of these molecular species required extraordinary sensitivity and precision. The James Webb Space Telescope's near-infrared spectrograph can detect the specific wavelengths of infrared light absorbed and emitted by different molecules in the comet's coma. Each molecule has a unique spectral fingerprint, allowing astronomers to not only identify what's present, but also measure relative abundances with remarkable accuracy. This chemical analysis represents one of the most detailed ever conducted of material from another star system. Every molecule detected in 3 I/Atlas's spectrum provides information about the conditions that existed in its birth environment billions of years ago, effectively giving us a chemical archaeology of ancient stellar systems. Fact 8. The Ancient Wanderer. Scientists believe 3 I/Atlas could be anywhere from 7 to 11 billion years old. To comprehend this age, consider that our entire solar system is only 4.6 billion years old. This means 3 I/Atlas was already ancient when the Sun was just forming from a collapsing cloud of gas and dust. It has witnessed the birth and death of countless stars, survived the galaxy's violent early history, and somehow remained intact throughout its incredible journey. The age estimation of 3 I/Atlas involves complex analysis of its trajectory through the galaxy and comparison with models of stellar populations and galactic evolution. Astronomers use a technique called kinematic age dating, which analyzes an object's motion through space to infer its likely origin and the time it has spent wandering through the galaxy. The high velocity of 3 I/Atlas, relative to the Sun about 58 kilometers per second, provides crucial information about its galactic history. Objects that formed early in the galaxy's history and have spent billions of years being scattered by gravitational encounters typically achieve higher velocities than younger objects. The specific velocity vector also suggests that 3 I/Atlas originated from the galaxy's thick disk, a population of stars that formed 8 to 12 billion years ago. If 3 I/Atlas is indeed 11 billion years old, it would have formed when the universe was only about 2.8 billion years old, roughly 20% of its current age. At that time, the galaxy was a very different place. Star formation rates were much higher, massive stars were more common, and the interstellar medium had a different chemical composition. The heavy elements that we take for granted today, including much of the carbon, oxygen, and other elements essential for planet formation, were still being produced and distributed by successive generations of stars. The survival of such an ancient object through billions of years of galactic evolution is remarkable in itself. During its journey, 3 I/Atlas would have encountered numerous potential hazards. close passes by massive stars, transits through dense molecular clouds, exposure to supernova shockwaves, and the general gravitational chaos of the galaxy's spiral arms. The fact that it has remained intact suggests either extraordinary luck or that interstellar space is less hostile to small bodies than we might expect. The age estimate also has implications for understanding planet formation around other stars. If 3I/Atlas formed 11 billion years ago, its parent star system would have formed from material that was significantly less enriched in heavy elements than the material that formed our Sun. This could explain some of its unusual chemical properties and suggests that planet formation processes in the early galaxy might have been quite different from what we observe today. The preservation of such ancient material also makes 3I/Atlas a potential time capsule from the early galaxy. The isotopic ratios and chemical compositions locked within its nucleus could provide direct information about conditions that existed when the Milky Way was young and actively forming most of its stellar population. Fact 9. A trajectory that tells tales. 3I/Atlas follows what astronomers call a hyperbolic trajectory, which is mathematical proof of its interstellar origin. Unlike the elliptical orbits of planets and solar system comets, a hyperbolic path means the object is moving too fast to be gravitationally bound to the Sun. It's a cosmic flyby that will last less than 2 years before 3I/Atlas disappears forever into the depths of space, carrying its secrets with it. The mathematics of orbital mechanics provide ironclad evidence for the interstellar nature of 3I/Atlas. In celestial mechanics, the shape of an orbit is characterized by a parameter called eccentricity. Circular orbits have an eccentricity of 0. Elliptical orbits have eccentricities between 0 and 1. Parabolic trajectories have an eccentricity of exactly 1. And hyperbolic trajectories have eccentricities greater than 1. The calculated eccentricity of 3I/Atlas's orbit is approximately 6.16, placing it firmly in the hyperbolic category. This extreme eccentricity means that 3I/Atlas is following what mathematicians call a hyperbola, one branch of a conic section. As it approaches the Sun, it will curve around our star and then recede into space along the other branch of the hyperbola, never to return. The total energy of the system, kinetic energy plus gravitational potential energy, is positive, which is the fundamental requirement for escape from the Sun's gravitational influence. Geometry of the trajectory provides additional clues about the object's galactic journey. When astronomers trace the orbit backward in time, accounting for the gravitational influences of the planets and the Sun's motion through the galaxy, they can estimate the direction from which 3I/Atlas approached our solar system. This analysis suggests it came from the general direction of the constellation Sagittarius, which points towards the center of our galaxy. However, determining the exact stellar system of origin is virtually impossible. As Harvard astronomer David Jewett noted, trying to trace the object's path back to its birth system is like glimpsing a rifle bullet for 1,000th of a second, and attempting to determine where it was fired from. The gravitational influences of countless stars, stellar clusters, and dark matter concentrations over billions of years have thoroughly scrambled any direct connection to its origin. The hyperbolic nature of the trajectory also determines the observational timeline for studying 3I/Atlas. The object will be closest to the Sun in late October 2025, after which it will begin its irreversible journey back to interstellar space. By 2027, it will likely be too faint for detailed observation, and within a few decades, it will be completely beyond the reach of our telescopes. The orbital inclination of approximately 175 degrees means that 3I/Atlas is moving in nearly the opposite direction to the planet's motion around the Sun. This retrograde motion is another strong indicator of its interstellar origin, as objects that formed within our solar system generally share similar orbital orientations with the planets. Fact 10. The thick disk connection. Based on its trajectory and velocity, astronomers believe 3 originated from the Milky Way's thick disk, a population of ancient stars that orbit above and below the main galactic plane where our Sun resides. The thick disk contains only 10 to 15% of our galaxy's stars, but these are among the oldest objects in the Milky Way. This makes 3I/8 our first close-up look at material from this ancient stellar population. Understanding the thick disk requires us to think about our galaxy's structure in 3 dimensions. Most people visualize the Milky Way as a flat spiral disk of stars, which is largely accurate for the majority of stellar populations. However, our galaxy actually consists of several distinct components. The thin disk where most stars reside, the thick disk of older stars, the central bulge, and the vast spherical halo that extends far beyond the visible galaxy. The thick disk formed during the early phases of galactic assembly, roughly 8 to 12 billion years ago. During this period, the galaxy was still actively accreting material and experiencing major merger events with smaller galaxies. The stars in the thick disk bear the chemical signatures of this violent early history. They typically have lower abundances of heavy elements compared to younger stars like our Sun, reflecting the fact that fewer generations of stellar nuclear synthesis had occurred when they formed. The orbital characteristics of thick disk stars are distinctly different from those in the thin disk. They have higher velocities relative to the galactic center, more eccentric orbits, and larger vertical excursions above and below the galactic plane. These properties suggest that thick disk stars experience significant gravitational perturbations during their formation epoch, possibly from galaxy mergers or interactions with massive dark matter substructures. The fact that 3I/Atlas likely originated from this population makes it an extraordinary astronomical find. We have never before had the opportunity to study material from the thick disk up close. All of our detailed knowledge of these ancient stellar populations comes from spectroscopic observations of distant stars. We can analyze their light and infer their properties, but we cannot directly sample their planetary systems or the comets that might have formed around them. The thick disk connection also provides context for understanding 3I/Atlas's unusual chemical composition. Stars in the thick disk formed from gas with different heavy element abundances than the material that created our solar system. This could explain why 3I/Atlas has such an extreme carbon dioxide to water ratio. It may reflect the different condensation chemistry that occurred in protoplanetary disks around ancient metal-poor stars. The vertical motion of 3I/Atlas through the galaxy is particularly telling. Computer models that trace its trajectory backward in time show that it has a high W velocity, the component of its motion perpendicular to the galactic plane. This is characteristic of thick disk objects, which spend significant portions of their orbits far above and below the main stellar disk. This vertical motion would have exposed 3I/Atlas to different gravitational influences and radiation environments compared to objects that remained closer to the galactic plane. The discovery of 3I/Atlas from the thick disk population has important implications for our understanding of interstellar object demographics. If thick disk stars can eject comets that survive for billions of years in interstellar space, then the population of wandering objects in our galaxy might be far more diverse and ancient than we previously imagined. This could revolutionize our understanding of how planetary systems evolve and how material is exchanged between different stellar populations over cosmic time. Fact 11. active far from home. Most comets don't show activity until they get relatively close to the Sun, typically within about 3 to 5 astronomical units. But 3I/Atlas began showing signs of a coma and outgassing when it was still 6 AU away farther out than Jupiter's orbit. This early activity suggests that its composition is fundamentally different from solar system comets, with materials that sublime at much lower temperatures. The early onset of cometary activity in 3Y/Atlas challenges our understanding of how comets typically behave. In our solar system, comets follow predictable patterns as they approach the Sun. At distances beyond about 5 AU, most comets remain dormant, with their volatile materials locked in solid form. As they move closer and solar heating increases, different materials begin to sublime. Carbon dioxide typically becomes active around 15 AU, carbon monoxide around 10 AU, and water ice around 3 AU. The fact that 3I/Atlas showed detectable activity at 6 AU, based on observations from NASA's TESS satellite, indicates that it contains materials with unusually low sublimation temperatures. This could be due to several factors. The comet might have an unusually high concentration of highly volatile materials, like carbon monoxide or nitrogen. It might have a very low density or porous structure that allows gases to escape more easily. Or it might contain exotic ices that don't exist in significant quantities in solar system comets. The early activity also suggests that 3Y/Atlas might have a different internal structure than typical comets. Many solar system comets develop protective crusts over time as they make repeated passages near the Sun. These crusts, composed of non-volatile materials left behind as ices sublime, can inhibit outgassing and cause comets to appear less active than they would be with fresh surfaces exposed. As an interstellar comet making its first and only passage through the inner solar system, 3I/Atlas likely has a pristine surface that allows easy escape of volatile materials. The TESS observations that detected this early activity required sophisticated analysis techniques. TESS is designed to monitor stars for transiting planets, not to track fast-moving comets. The spacecraft's cameras capture the same regions of sky for 27 days at a time, which is ideal for detecting the periodic dimming caused by planets, but not optimal for following moving objects like comets. Astronomers had to use image stacking techniques to follow 3I/Atlas across multiple TESS images, essentially creating a time-lapse movie of the comet's motion and brightness changes. The coma detected by TESS had a radius of approximately 23 kilometers when the comet was 6 AU from the Sun. This might seem small, but for such a distant and cold environment, it represents significant activity. The production of gas and dust at this distance requires a substantial amount of energy input, either from solar heating or from internal processes within the comet. This early activity has important implications for understanding the comet's total volatile content and its potential behavior as it continues to approach the Sun. If 3I/Atlas is already active at 6 AU, it might develop spectacular cometary features, an extensive coma, and possibly multiple tails as it reaches perihelion. Alternatively, if it has a limited volatile content, the early activity might represent the beginning of a process that will consume most of its volatile materials before reaching closest approach to the Sun. The timing of the activity onset also provides clues about the comet's thermal properties. Different materials have different sublimation curves, the relationship between temperature and the rate at which they transition from solid to gas. By carefully monitoring how 3I/Atlas's activity level changes with solar distance, astronomers can infer the composition and abundance of different volatile materials in its nucleus. Fact 12. A dust cloud of extraordinary proportions. The coma surrounding 3Y/Atlas extends for at least 348,000 kilometers, nearly the distance from Earth to the Moon. This enormous envelope of gas and dust is primarily composed of carbon dioxide, creating a massive, invisible cloud that's completely transparent to visible light, but glows brilliantly in infrared wavelengths that only space telescopes can detect. The scale of this coma is truly staggering when compared to typical cometary phenomena. Even the most spectacular comets visible from Earth, such as Comet Hale-Bopp or Comet Neowise, typically have comae that extend for tens of thousands of kilometers. The fact that 3A/Atlas has produced a coma nearly 10 times larger than typical bright comets, while still relatively far from the Sun, suggests either an unusually active nucleus or a composition that produces gas at unusually high rates. The carbon dioxide dominance of this vast coma makes it largely invisible to traditional optical telescopes. Carbon dioxide doesn't emit or absorb light strongly in the visible spectrum, which is why the comet appears relatively faint despite its enormous gas production. However, CO2 has strong absorption and emission features in the infrared portion of the electromagnetic spectrum, making it easily detectable by space-based infrared telescopes like the James Webb Space Telescope and SPHEREX. The detection of this extended coma required sophisticated observational techniques and data analysis. NASA's SPHEREX, spectrophotometer for the history of the universe, epoch of reionization and ICE's Explorer. Observatory used its wide-field infrared imaging capabilities to map the full extent of the CO2 cloud. By observing at specific infrared wavelengths where carbon dioxide absorbs and emits light, SPHEREX could distinguish the comet's coma from the background sky and measure its size and brightness distribution. The physical processes that create and maintain such an extended coma involve complex interactions between solar radiation, the solar wind, and the gas and dust expelled from the comet's nucleus. As volatile materials sublime from the nucleus, they carry dust particles with them, creating a mixture of gas and solid particles. Solar radiation pressure and the solar wind. The stream of charged particles flowing from the sun then interact with this material, shaping it into the characteristic cometary coma and tail structures. The transparency of the coma to visible light has important observational implications. Unlike dust-rich comets that can appear bright due to sunlight scattered by solid particles, 3Y/Atlas remains relatively faint in visible light despite its enormous gas production. This means that amateur astronomers and small telescopes might struggle to observe impressive visual displays from this comet, even though professional instruments detect intense activity. The composition of the coma also provides a window into the nucleus composition and the processes occurring on its surface. The gas molecules detected in the coma, primarily CO2, but also water, carbon monoxide, and other species, originate from ices within the nucleus that sublime as solar heating increases. By studying the relative abundances and spatial distribution of these molecules in the coma, astronomers can infer the composition and structure of the nucleus itself. The temporal evolution of the coma size and brightness offers additional insights into the comet's behavior. As 3I/Atlas continues to approach the Sun, solar heating will increase, potentially leading to more extensive outgassing and coma development. Monitoring these changes allows astronomers to understand how the comet responds to changing thermal conditions and to predict its future behavior. The vast scale of the coma also has implications for spacecraft missions and planetary defense considerations. While 3I/Atlas poses no threat to Earth, future interstellar visitors might come closer to our planet. Understanding how such objects can produce extensive, largely invisible envelopes of gas and dust is important for accurately assessing any potential hazards they might pose. Fact 13. The retrograde rebel. 3I/Atlas doesn't play by our solar system's rules. Its orbit is inclined about 175 degrees to the ecliptic plane, meaning it's moving in nearly the opposite direction to all the planets. This retrograde motion is another clear signature of its interstellar origin, and suggests it approached our solar system from a completely different angle than anything that formed here. The concept of orbital inclination is fundamental to understanding how objects move through space. In our solar system, most objects orbit the Sun in roughly the same plane, called the ecliptic, which is defined by Earth's orbital path. This common orbital orientation reflects the way our solar system formed from a rotating disk of gas and dust 4.6 billion years ago. The conservation of angular momentum ensured that most objects ended up orbiting in the same direction and roughly the same plane. When astronomers measure orbital inclinations, they use the ecliptic plane as a reference. An inclination of 0 degrees means an object orbits in exactly the same plane as Earth, while 90 degrees indicates an orbit perpendicular to the ecliptic. Inclinations greater than 90 degrees indicate retrograde motion. The object is orbiting in the opposite direction to the planets. With an inclination of approximately 175 degrees, 3I/Atlas is moving almost exactly opposite to the planetary motion. This is extraordinarily unusual for objects that formed within our solar system. Even the most highly inclined solar system objects, such as certain Kuiper belt objects or long-period comets from the Oort cloud, rarely exceed inclinations of 140, 150 degrees. The retrograde motion of 3I/Atlas provides compelling evidence for its interstellar origin, but it also tells us something about its journey through the galaxy. The fact that it approaches our solar system head-on suggests that it wasn't simply following a similar orbital path around the galactic center. Instead, its trajectory indicates a complex history of gravitational interactions that have scattered it into a highly inclined orbit relative to the galactic disk. This orbital geometry also affects the observational opportunities for studying 3I/Atlas. Because it's moving retrograde relative to Earth's motion, the relative velocity between our planet and the comet is higher than it would be for a prograde visitor. This means that the observational window is compressed. The comet appears to move more rapidly across our sky, giving astronomers less time to study it in detail. The retrograde motion also influences how 3I/Atlas interacts with the solar wind and interplanetary magnetic field. The solar wind flows radially outward from the Sun, creating a complex magnetic environment throughout the solar system. Objects moving in retrograde orbits encounter this environment from a different angle than prograde objects, potentially leading to different patterns of cometary activity and tail development. From a perspective, the high inclination of 3I/Atlas makes it less likely to experience close encounters with the giant planets during its passage through the solar system. Objects with orbital inclinations close to the ecliptic plane have higher probabilities of passing near Jupiter, Saturn, or other massive planets, which can significantly alter their trajectories through gravitational interactions. The nearly polar orbit of 3I/Atlas largely isolates it from such influences, allowing it to follow a more predictable path determined primarily by the Sun's gravity. The retrograde nature of the orbit also provides constraints on possible formation mechanisms for interstellar objects. In stellar systems, where planets form in orderly coplanar configurations like our solar system, ejecting objects into highly inclined or retrograde trajectories requires specific mechanisms such as planet scattering, stellar encounters, or dynamical instabilities. The fact that we observe retrograde interstellar visitors suggests that chaotic dynamical processes are common during planetary system evolution. Fact 14. Speed that defies comprehension. Before entering our solar system, 3WAIN/Atlas was traveling at about 60 kilometers per second relative to the Sun. That's roughly 134,000 miles per hour, fast enough to travel from New York to Los Angeles in about 90 seconds. This incredible velocity accumulated over billions of years as the object was gravitationally accelerated by countless encounters with stars, stellar clusters, and massive molecular clouds throughout the galaxy. To truly appreciate the magnitude of this velocity, it's helpful to compare it to other high-speed phenomena we might be familiar with. The International Space Station orbits Earth at about 7.6 kilometers per second, or roughly 17,000 miles per hour. NASA's Parker Solar Probe, currently the fastest human-made object, reaches speeds of about 200 kilometers per second at its closest approach to the Sun. 3I/Atlas, traveling at 60 kilometers per s through interstellar space, is moving at roughly one-third the speed of humanity's fastest spacecraft, but it has maintained this velocity for billions of years without any propulsion system. The physics behind achieving such extreme velocities in interstellar space involves a process called gravitational acceleration, or gravitational slingshot effects, but on a galactic scale. Each time 3I/Atlas passed near a massive object, a star, stellar cluster, or dense molecular cloud, it experienced a gravitational interaction that could either increase or decrease its velocity, depending on the geometry of the encounter. Over billions of years and countless such encounters, 3I/Atlas gradually accumulated kinetic energy. This process is somewhat similar to a pinball bouncing around a machine, gaining energy with each collision, except that in the case of 3I/Atlas, the collisions were gravitational encounters that didn't require physical contact. The most significant velocity increases likely occurred during close encounters with massive stars or passages through dense stellar environments such as the cores of globular clusters or the central regions of the galaxy. The specific velocity of 60 kilometers per s relative to the Sun is also significant in the context of galactic astronomy. This speed places 3I/Atlas in what astronomers call the high-velocity tail of stellar motions in our galaxy. While typical stars near the Sun move at velocities of 20 to 40 kilometers per s relative to the local standard of rest, objects with velocities exceeding 50 to 60 kilometers per s are relatively rare and usually associated with old stellar populations such as the thick disk or halo. The velocity measurement itself represents a remarkable achievement in observational astronomy. To determine that 3I/Atlas is moving at 60 kilometers per s relative to the Sun, astronomers must precisely measure its position against the background stars over time, account for Earth's motion around the Sun, correct for the Sun's motion through the galaxy, and apply relativistic corrections for the high velocities involved. This requires extraordinary precision in both observation and calculation. The high velocity of 3I/Atlas also has implications for its detectability and the duration of its visit to our solar system. High-velocity objects spend less time within the observable volume around the Sun, making them more challenging to detect and study. The fact that we've now discovered 3 interstellar objects, all with relatively high velocities, suggests that such objects might be more common than previously thought, but their rapid transit through our neighborhood makes them difficult to find. As 3I/Atlas continues its journey through our solar system, its velocity relative to the Sun will change due to gravitational acceleration. At perihelion, it will be moving fastest, potentially reaching speeds of over 70 kilometers per s. As it recedes from the Sun, it will slow down but will still retain a substantial velocity when it eventually exits our solar system and returns to interstellar space. The long-term trajectory of 3I/Atlas after it leaves our solar system is equally fascinating to consider. With its high velocity, it will continue traveling through the galaxy, potentially encountering other star systems over the coming millions and billions of years. The gravitational influence of our Sun will slightly modify its path, but this change will be minimal compared to the object's enormous kinetic energy. Fact 15. The Sagittarius connection, 3I/Atlas, approached our solar system from the direction of the constellation Sagittarius, which happens to be the direction of our galaxy's center. While this doesn't necessarily mean it came from the galactic core, it does suggest that the object's journey may have taken it through some of the most dense and active of the Milky Way, where it could have encountered numerous gravitational influences. Sagittarius holds special significance in galactic astronomy because it contains the direction to the Milky Way's central supermassive black hole, known as Sagittarius A*, pronounced Sagittarius A star. This region of the sky is home to the galactic center, the central molecular zone with its complex chemistry and extreme physical conditions, and some of the most massive stellar clusters in our galaxy. The fact that 3I/Atlas approached from this direction suggests it may have experienced some of the most dynamically intense environments our galaxy has to offer. The galactic center region is characterized by extreme density gradients, intense radiation fields, and complex gravitational dynamics. Within a few hundred light-years of the central black hole, stellar densities are millions of times higher than in the solar neighborhood. Massive stars form and evolve rapidly in this environment, creating frequent supernovae and stellar winds that can dramatically alter the trajectories of passing objects. The central molecular zone surrounding the galactic center contains vast reservoirs of molecular gas with unusual chemical compositions compared to the material in our local galactic neighborhood. Objects passing through these regions could potentially accrete material with different isotopic ratios and chemical signatures than those found in the outer galaxy, where our solar system resides. This could partially explain some of the unusual chemical properties observed in 3I/Atlas. However, it's important to note that the apparent approach direction doesn't necessarily indicate the object's ultimate origin. Over billions of years of galactic travel, the trajectory of 3I/Atlas would have been modified by countless gravitational encounters. The direction from which it currently approaches our solar system reflects its most recent path through the galaxy rather than its birthplace. Tracing the object's trajectory backward more than a few million years becomes increasingly uncertain due to the chaotic nature of galactic dynamics. The Sagittarius direction is also significant because it's the location of several major stellar streams and tidal debris from disrupted satellite galaxies. The Milky Way has been accreting smaller galaxies throughout its history, and the gravitational interactions involved in these merger events create complex patterns of stellar motion. Objects ejected from disrupted satellite galaxies could potentially become interstellar wanderers with unusual velocity distributions and approach directions. Recent observations of 3I/Atlas have attempted to determine whether its chemical composition shows any signatures that might be associated with the galactic center region. The high CO2/H2O ratio could potentially be explained by formation in an environment with different stellar populations and feedback processes than those in the outer galaxy. However, establishing such connections requires extremely detailed chemical analysis and comparison with models of galactic chemical evolution. The approach direction also affects the observational geometry for studying 3I/Atlas. Objects approaching from the direction of the galactic center must be observed against the background of the galactic plane, where stellar densities are high and extinction from interstellar dust can complicate observations. This makes precision astrometry and photometry more challenging compared to objects that approach from directions perpendicular to the galactic plane. From the perspective of galactic archaeology, the Sagittarius approach direction adds another layer of interest to 3I/Atlas. This object potentially carries information not just about its original stellar system, but also about the various galactic environments it has traversed during its journey. The chemical and isotopic signatures locked within its nucleus could preserve evidence of interactions with interstellar material from some of the most exotic regions of our galaxy. Fact 16. A discovery window measured in months. Unlike planets or asteroids that we can observe for years or decades, 3I/Atlas presents a fleeting opportunity for study. From its discovery in July 2025 to when it disappears behind the Sun in late October, astronomers have only a few months to gather as much data as possible. After its closest approach to the Sun, it will become visible again in December 2025, but it will be rapidly fading as it heads back to interstellar space. The compressed observational timeline creates unprecedented urgency in the astronomical community. Typically, when astronomers discover a new comet or asteroid, they have years or even decades to plan detailed observations, secure telescope time, and develop comprehensive research programs. The discovery of 3I/Atlas triggered an immediate scramble to redirect major observatories and space missions towards this fleeting target. The initial observational window from July through October 2025 is particularly crucial because this is when 3I/Atlas is approaching the Sun and becoming more active. As solar heating increases, the comet's outgassing will intensify, potentially revealing new molecular species and providing insights into the composition and structure of its nucleus. This inbound phase offers the best opportunity to study how an interstellar comet responds to increasing solar radiation. The timing constraints have forced astronomers to prioritize observations carefully. Every clear night represents a precious opportunity to gather data that may never be obtainable again. Major observatories around the world have dedicated significant telescope time to 3I/Atlas, sometimes bumping other scheduled observations to accommodate this rare visitor as soon. The October solar conjunction presents a particular challenge for ground-based observations. As 3I/Atlas approaches its closest point to the Sun, it will gradually disappear into the solar glare, becoming impossible to observe from Earth-based telescopes. This means that the period of maximum cometary activity, when 3I/Atlas should be brightest and most spectacular, will be largely hidden from direct observation. Space-based observatories offer some advantages during this period. Telescopes like the Solar and Heliospheric Observatory, SOHO, and the Parker Solar Probe are specifically designed to observe the region near the Sun, and might be able to track 3I/Atlas even when it's invisible from Earth. However, these instruments have limited capabilities compared to major ground-based telescopes, so the solar conjunction still represents a significant observational gap. The post-perihelion observational window beginning in December 2025 presents both opportunities and challenges. On the positive side, 3I/Atlas will have experienced maximum solar heating and may display the full range of its cometary activity. The comet may have developed spectacular tails and could potentially be visible to amateur astronomers if it becomes bright enough. However, the post-perihelion period also brings rapid fading as the comet recedes from the Sun. Unlike periodic comets that make repeated visits and can be studied over multiple apparitions, 3I/Atlas is making its one and only passage through the inner solar system. As it moves away from the Sun, solar heating decreases, outgassing diminishes, and the comet becomes progressively fainter and more difficult to observe. The fading timeline depends partly on the comet's actual size and volatile content, both of which remain uncertain. If 3I/Atlas has abundant volatile materials, it might remain active and observable for many months after perihelion. Alternatively, if it has limited volatile reserves or develops a protective crust, it could fade rapidly, providing only a brief post-perihelion observational window. By mid-2026, most ground-based telescopes will likely lose the ability to detect 3I/Atlas, though the largest instruments might be able to track it for somewhat longer. Space-based telescopes with superior sensitivity might extend observations into 2027 or beyond, but even these observations will become increasingly challenging as the comet fades. The time pressure has also accelerated international collaboration in ways rarely seen in astronomy. Research teams that might normally compete for telescope time and publication priority have formed unprecedented collaborations to maximize the scientific return from this fleeting opportunity. Data sharing agreements, joint observing proposals, and coordinated observation campaigns have emerged rapidly to ensure that no opportunities are missed. Fact 17. The magnitude challenge. At magnitude 18.5,3 I/Atlas is incredibly faint, about 2.5 million times dimmer than Polaris, the North Star. This means that even with the most powerful amateur telescopes, it appears as nothing more than a tiny, barely detectable point of light. Only the world's largest professional observatories and space telescopes can capture detailed images and spectra of this ancient visitor. The astronomical magnitude system, which measures the brightness of celestial objects, is logarithmic and somewhat counterintuitive. Lower magnitude numbers correspond to brighter objects, while higher numbers indicate fainter objects. The scale is calibrated so that a difference of 5 magnitudes corresponds to a factor of 100 in brightness. This means that magnitude 18.5 is exactly 2.512 circumflex 18, 2.5 million times fainter than magnitude 0. To put this extreme faintness in perspective, consider that the faintest stars visible to the naked eye under perfect dark skies are around magnitude 6.5. Advanced amateur telescopes can typically reach objects as faint as magnitude 14, 15 under excellent conditions. Professional ground-based telescopes can detect objects down to magnitude 24, 26, while space telescopes can push even fainter. At magnitude 18.5,3 I/Atlas sits in the realm that requires serious professional equipment to observe effectively. The faintness of 3I/Atlas creates numerous observational challenges beyond simple detection. Obtaining detailed spectra measurements of how the object's brightness varies with wavelength requires collecting substantial amounts of light. With such a faint source, this means either using very large telescopes or integrating observations over long periods of time. Both approaches have limitations. Large telescopes have limited availability and high demand, while long integrations risk losing the object as it moves across the sky. The faint magnitude also makes 3I/Atlas vulnerable to observational bias effects. Earth's atmosphere constantly fluctuates, causing star images to dance and blur, the phenomenon astronomers call seeing. For very faint objects, poor seeing can cause the light to be spread over a larger area, making detection even more difficult. This is why the world's premier observatories are located at sites with exceptional atmospheric stability, such as Mauna Kea in Hawaii or the Atacama Desert in Chile. Light pollution presents another significant challenge for observing such a faint object. Even at professional observatories, the growing problem of artificial light pollution can interfere with observations of very faint objects. The scattered light from distant cities creates a background glow that can overwhelm the faint signal from objects like 3I/Atlas. This makes dark sites increasingly valuable for studying such objects. The imaging challenges extend beyond simple brightness considerations. Because 3I/Atlas is moving relatively rapidly across the sky, conventional photographic techniques that work well for stationary objects become complicated. Long exposures that might be used to accumulate light from a faint star will show 3E/Atlas as a streak rather than a point source. This requires specialized tracking techniques or image processing methods to follow the comet's motion during the exposure. Space-based telescopes offer significant advantages for observing faint objects like 3Y/Atlas. Without atmospheric interference, space telescopes can achieve better image quality and more stable photometry. They're also not subject to day-night cycles, allowing for continuous observation when the target is properly positioned. However, space telescope time is extremely valuable and heavily oversubscribed, making it challenging to secure sufficient observing time for comprehensive studies. The faintness of 3I/Atlas also affects the types of scientific measurements that are possible. Detailed spectroscopy, which can reveal the chemical composition of the comet's coma and provide insights into nuclear composition, requires substantial signal-to-noise ratios. With such a faint object, obtaining high-quality spectra becomes a significant technical challenge that may require innovative observational strategies or instrumentation. Despite these challenges, the faintness of 3I/Atlas also provides scientific information in itself. The brightness of a comet depends on several factors: the size of its nucleus, the reflectivity of its surface materials, and the amount of gas and dust it's producing. By carefully measuring the total brightness and how it changes with solar distance, astronomers can constrain these physical properties and better understand the nature of this interstellar visitor. The magnitude measurements also provide crucial data for understanding the population of interstellar objects in general. If objects like 3I/Atlas are typically this faint, it suggests that many more such visitors may pass through our solar system undetected. Future sky surveys with greater sensitivity might reveal a much larger population of interstellar objects, revolutionizing our understanding of how common such visitors actually are. Fact 18. The teardrop mystery. When Hubble Space Telescope captured its sharpest image of 3I/Atlas on July 21, 2025, it revealed something peculiar, a teardrop-shaped cocoon of dust, but not where you'd expect it. Instead of trailing behind the comet as dust tails normally do, the brightest concentration appeared to be in front of the nucleus, toward the Sun. This unusual configuration suggests that the dust might actually be fragments of ice that evaporate quickly before they have time to form a traditional tail. This discovery challenges fundamental assumptions about how comets behave as they approach the Sun. In typical comets, solar radiation pressure pushes dust particles away from the Sun, creating the characteristic tail that always points away from our star, regardless of the comet's direction of motion. The physics behind this is straightforward. Photons from sunlight carry momentum, and when they strike dust particles, they impart a small but measurable force that accelerates the particles away from the Sun. The teardrop shape observed in 3I/Atlas suggests a more complex process is occurring. The leading hypothesis is that instead of producing durable dust particles that can survive long enough to form extended tails, 3I/Atlas is ejecting fragments of ice that quickly sublime in the solar radiation field. These ice fragments would initially move away from the nucleus in all directions due to the gas pressure created by sublimation, but they would evaporate within hours or days of being expelled. This rapid sublimation process could create the unusual brightness distribution observed by Hubble. The ice ejection, when they're still substantial enough to scatter significant amounts of sunlight. As they sublime away, they would fade rapidly, creating a brightness gradient that peaks near the nucleus and falls off quickly with distance. The implications of this interpretation are profound for understanding the composition and structure of 3I/Atlas. If the object is indeed ejecting ice fragments rather than conventional dust, it suggests that its nucleus has an unusually high volatile content, or that its internal structure allows easy access of subsurface ices to the surface. Most comets develop mantles of non-volatile material over time, but as a first-time visitor to the inner solar system, 3I/Atlas might have a pristine surface that allows direct sublimation of subsurface ices. The Hubble observations were particularly challenging to obtain because 3I/Atlas is moving rapidly across the sky relative to background stars. To capture sharp images of the comet, Hubble had to track the object's motion precisely, which meant that background stars appeared as streaks in the final images. This tracking capability is one of Hubble's unique strengths, allowing it to observe moving objects with the same resolution it achieves for stationary targets. The teardrop morphology also provides clues about the nucleus's rotation state and the distribution of active regions on its surface. If outgassing were occurring uniformly across the nucleus, we would expect to see a more symmetric coma. The asymmetric teardrop shape suggests that gas and ice production is concentrated in specific regions, possibly related to the orientation of the nucleus's rotation axis or the distribution of volatile materials beneath the surface. Temperature modeling of the nucleus provides additional context for understanding this unusual behavior. As 3I/Atlas approaches the Sun, different regions of its surface experience varying levels of solar heating depending on the nucleus's shape, rotation period, and orientation. Areas that receive more direct sunlight would experience higher temperatures and more intense sublimation, potentially creating the asymmetric outgassing pattern observed by Hubble. The rapid sublimation of ice fragments also has implications for understanding the total mass loss rate from 3I/Atlas. Traditional dust production models assume that solid particles can survive for extended periods after ejection, allowing them to form large, persistent Comet tails. If 3I/Atlas is instead producing primarily ice fragments that sublime quickly, the total mass loss rate might be higher than estimates based purely on the visible Comet extent. Fact 19. The invisible giant. Even with Hubble's incredible resolution, astronomers cannot directly see the solid nucleus of 3I/Atlas. What we observe is the glow from the enormous coma surrounding the nucleus, making it nearly impossible to determine the exact size of the actual solid body. This is like trying to measure a flashlight bulb while it's surrounded by a massive, glowing fog. You can see the light, but the source remains hidden. The challenge of nucleus detection in active comets is one of the fundamental difficulties in cometary astronomy. When comets approach the Sun and begin outgassing, they develop extensive atmospheres that can be thousands of times larger than the solid nucleus itself. The light we observe from Earth comes primarily from sunlight scattered by dust particles and gas molecules in this atmosphere, not from reflected sunlight off the nucleus surface. In the case of 3I/Atlas, the situation is particularly complex because of its unusual composition and activity patterns. The carbon dioxide-dominated coma is largely transparent to visible light, but contains enough dust and other materials to create a diffuse glow that completely overwhelms any direct signal from the nucleus. Advanced image processing techniques have been applied to try to isolate the nucleus signal, but the contrast ratio between the coma brightness and any potential nucleus detection remains too high for current instruments. The nucleus detection problem is further complicated by the unknown shape and rotation state of 3I/Atlas. Most comet nuclei are irregular potato-shaped objects with rotation periods ranging from a few hours to several days. As these objects rotate, different surface features come into view, potentially causing brightness variations that could be detected if the nucleus were visible. However, with the nucleus completely obscured by its coma, these potential rotation signatures are lost in the much brighter atmospheric glow. Theoretical modeling provides some constraints on the nucleus properties based on the observed coma characteristics. The total brightness of the coma, combined with assumptions about dust production rates and gas-to-dust ratios, allows astronomers to estimate the minimum nucleus size required to sustain the observed activity. These models suggest that 3I/Atlas likely has a nucleus at least several kilometers in diameter, but they cannot provide definitive upper limits without direct detection. The nucleus obscuration also affects our understanding of the object's thermal properties and internal structure. Direct infrared observations of comet nuclei can reveal information about surface temperature, thermal inertia, and the presence of different surface materials. With the nucleus hidden behind its coma, these measurements become impossible, forcing astronomers to rely on indirect methods and theoretical models. Sophisticated deconvolution techniques have been attempted to try to separate nucleus contributions from coma emission in the Hubble images. These mathematical procedures attempt to model the expected brightness distribution of the coma and subtract it from the observed images, potentially revealing a residual point source that could represent the nucleus. However, these techniques are limited by uncertainties in coma modeling and instrument resolution, and they have not yet produced definitive nucleus detections for 3I/Atlas. The nucleus detection challenge has important implications for mission planning and spacecraft observations. If future interstellar objects are discovered early enough to allow spacecraft missions, the ability to directly image and characterize the nucleus would provide invaluable scientific data. However, the experience with 3I/Atlas demonstrates that even close spacecraft approaches might need to account for extensive comae that could obscure the nucleus during periods of high activity. Future technological developments might eventually allow nucleus detection even in highly active comets. Advanced coronagraphic techniques, developed primarily for exoplanet detection, could potentially suppress coma brightness enough to reveal underlying nuclei. Similarly, observations at wavelengths where coma emission is minimal might provide opportunities for direct nucleus detection. The invisible nucleus problem also highlights the limitations of remote observations compared to in situ measurements. While telescopes can provide detailed information about coma composition and dynamics, understanding the fundamental properties of interstellar objects may ultimately require direct spacecraft encounters that can penetrate the coma and observe the nucleus at close range. Fact 20. Carbon dioxide dominance. The chemical analysis of 3I/Atlas reveals a composition that's almost alien by solar system standards. NASA's Spherex Observatory detected a carbon dioxide coma that extends for hundreds of thousands of kilometers, while water vapor signatures are surprisingly weak. This is the complete opposite of what we see in comets from our own solar system, where water typically dominates the composition. The extreme CO2/H2O ratio of approximately 8, one observed in 3I/Atlas, represents one of the most unusual chemical signatures ever detected in a comet. To understand how remarkable this is, consider that typical solar system comets show CO2/H2O ratios of about 0.1 to 0.3, meaning water is usually 3 to 10 times more abundant than carbon dioxide. The composition of 3I/Atlas is completely inverted from this norm, suggesting formation conditions that were dramatically different from those in our solar system. The detection of this chemical anomaly required sophisticated space-based spectroscopy capabilities. Spherex, spectrophotometer for the history of the universe, epoch of reionization and ICES Explorer, uses its wide-field infrared imaging spectrometer to map the sky at 102 different wavelengths between 0.75 and 5.0 microns. This wavelength range is ideal for detecting the vibrational and rotational transitions of molecules like CO2 and H2O, which have strong absorption and emission features in the near and mid-infrared. The carbon dioxide dominance has profound implications for understanding the formation environment of 3i/8-less. In protoplanetary disks around young stars, the condensation of different molecular species depends critically on temperature and pressure conditions. Water ice typically condenses at temperatures around 150, 170 Kelvin, while CO2 ice requires somewhat cooler conditions, around 80, 100 Kelvin, depending on the local pressure and gas composition. The fact that 3i/Atlas is so rich in CO2 relative to H2O suggests several possible formation scenarios. It might have formed in a region of its parent protoplanetary disk where temperatures were too warm for significant water ice condensation, but still cool enough for CO2 ice formation. Alternatively, it could have formed around a star with different luminosity and spectral characteristics than our Sun, creating different temperature profiles in the surrounding disk. Another possibility is that 3i/8-less formed in an environment with unusually high CO2 abundance in the gas phase. The carbon and oxygen chemistry in protoplanetary disks can be influenced by the metallicity of the parent star, the presence of other massive planets that might alter the chemical composition through dynamical processes, or unique chemical processing pathways that were more common in the early galaxy when 3i/Atlas likely formed. The preservation of this unusual composition over billions of years of interstellar travel is itself remarkable. Cosmic ray processing, interactions with interstellar magnetic fields, and collisions with dust grains can gradually alter the surface chemistry of interstellar objects. The fact that 3i/Atlas still shows such extreme CO2 dominance suggests either that these processing effects are less significant than previously thought, or that the object has sufficient internal reserves to maintain its unusual surface composition. The CO2 dominance also affects the physical behavior of 3i/Atlas as it approaches the Sun. Carbon dioxide has different sublimation properties than water ice, becoming active at greater distances from the Sun and producing different gas expansion dynamics. This helps explain why 3i/Atlas became active unusually early in its approach, when it was still beyond Jupiter's orbit. The detection of such high CO2 concentrations has important implications for astrobiology and the study of organic chemistry in space. While CO2 itself is not a biological indicator, its presence in high concentrations suggests specific chemical environments that could be relevant for understanding the distribution of carbon-bearing molecules throughout the galaxy. The study of 3i/8-less provides insights into carbon chemistry processes that occurred around ancient stars, potentially informing our understanding of how organic molecules were distributed in the early universe. Fact 21. The nickel surprise. Among the most intriguing discoveries in 3i/Atlas's spectrum is the presence of nickel, but not just any nickel. The spectral signatures suggest nickel without iron, similar to what we see in industrial nickel alloy production, through a specific chemical pathway called the carbonyl process. This has led to wild speculation about the comet's true nature. Though most scientists believe it's a natural phenomenon, we simply don't yet understand. The detection of nickel in cometary spectra is not entirely unprecedented, but it is unusual. Nickel has been detected in a small number of solar system comets, typically in very low concentrations and usually associated with iron in mineral phases that reflect the object's formation from processed stellar material. However, the nickel signatures in 3I/Atlas appear to be different, showing spectral characteristics that suggest metallic nickel or nickel-rich phases that are not commonly observed in natural solar system objects. The carbonyl process reference relates to an industrial method for purifying nickel, where nickel tetracarbonyl, NiCO4, is formed at relatively low temperatures and then decomposed at higher temperatures to deposit pure metallic nickel. This process is used in manufacturing because it can produce very pure nickel without ion contamination. The spectral similarities between the nickel signatures in 3I/Atlas and industrially processed nickel have inevitably led to speculation about artificial origins, though such explanations remain highly speculative and lack supporting evidence. From a more conventional astrophysical perspective, the unusual nickel signatures might reflect unique chemical processing pathways that occurred during the formation or evolution of 3I/Atlas. In the extreme environments around certain types of stars, particularly Wolf-Rayet stars or the evolved cores of massive stars, nuclear processing can create unusual isotopic ratios and elemental abundances that differ significantly from solar system norms. The formation of metallic phases in cometary materials typically requires specific conditions of temperature, pressure, and chemical environment. In most solar system formation scenarios, nickel is incorporated into silicate minerals or iron-nickel alloys similar to those found in meteorites. The apparent lack of associated iron signatures in 3I/Atlas suggests either a formation environment with unusual iron depletion or post-formation processing that separated nickel from iron-bearing phases. Cosmic ray processing during billions of years of interstellar travel could potentially create unusual nuclear chemistry effects. High-energy cosmic rays can induce nuclear reactions in solid materials, potentially creating unusual isotopic ratios or even transmuting elements under extreme circumstances. While such effects are generally considered minor for most materials, the unique exposure history of 3I/Atlas might have resulted in unusual chemical modifications. The nickel detection also raises questions about the sensitivity limits and interpretation of spectroscopic observations. Detecting specific metallic phases in the diffuse, low-density environment of a cometary coma requires extremely sensitive instruments and careful analysis to distinguish real signals from instrumental artifacts or contamination from other sources. The spectroscopic techniques used to detect nickel in 3I/Atlas involve analyzing the absorption and emission lines created when atoms and molecules interact with sunlight and solar radiation. Different elements and chemical phases produce characteristic spectral signatures, but interpreting these signatures in the complex environment of a cometary coma requires sophisticated modeling of excitation processes, temperature distributions, and chemical kinetics. The unusual nickel chemistry in 3I/Atlas adds to the growing body of evidence that this object formed in an environment significantly different from our solar system. Combined with the extreme CO2/H2O ratio and other chemical anomalies, the nickel signatures paint a picture of an object that experienced formation and evolution processes that have no close analogues in our local cosmic neighborhood. Future observations with increasingly sensitive spectroscopic capabilities may help resolve the nature of the nickel signatures in 3I/Atlas and determine whether similar chemical anomalies exist in other interstellar objects. These measurements could provide crucial insights into the diversity of chemical processes that occur in different stellar environments and the range of conditions that can exist in planetary systems throughout the galaxy. Fact 22. A comet that breaks the rules. Traditional comets follow predictable patterns. They develop visible tails and comas as they approach the Sun, with activity peaking near perihelion. But 3I/Atlas started showing activity at unprecedented distances and maintains a composition that defies our understanding. It's almost as if the universe is presenting us with a completely new type of cosmic object that doesn't fit into our existing categories. The conventional model of cometary behavior, developed through centuries of observations of solar system comets, provides a framework for understanding how these objects should behave as they approach the Sun. This model predicts that comets remain essentially dormant until they reach distances of about 5 astronomical units from the Sun, at which point solar heating becomes sufficient to sublime water ice and create detectable comae and tails. The model further predicts that cometary activity should increase smoothly as solar distance decreases, with different volatile materials becoming active at characteristic distances. Carbon dioxide typically becomes active first, around 15 to 20 AU, followed by carbon monoxide around 10 to 15 AU, and finally water ice around 3 to 5 AU. The relative abundances of these materials in typical solar system comets create predictable patterns of brightness, evolution, and spectral signatures. 3I/Atlas violates virtually every aspect of this traditional model. It became active at distances where most comets remain completely dormant. It shows chemical compositions that are completely inverted from solar system norms, and its brightness evolution follows patterns that don't match standard cometary models. These deviations are so extreme that they force astronomers to reconsider fundamental assumptions about what constitutes normal cometary behavior. The rule-breaking behavior of 3I/Atlas also extends to its physical properties. Most solar system comets show evidence of layered internal structures, with different volatile materials distributed at different depths beneath protective surface crusts. The outgassing patterns of 3I/Atlas suggest either a very different internal structure or surface properties that allow easy access of subsurface materials to the solar radiation field. The temporal evolution of 3I/Atlas's activity also defies conventional expectations. Rather than showing the smooth increase in activity that characterizes most solar system comets, 3I/Atlas appears to have become active relatively suddenly when it was discovered, suggesting that its response to solar heating follows different physical processes than those observed in familiar comets. These anomalous behaviors have forced astronomers to develop new theoretical frameworks for understanding interstellar objects. The possibility that objects from other stellar systems might have fundamentally different compositions, structures, and behaviors was anticipated, but the extent of the differences observed in 3I/Atlas exceeds most theoretical predictions. The rule-breaking nature of 3I/Atlas also highlights the limitations of our current understanding of cometary physics. Most cometary models are based on observations of objects that formed in our solar system under specific conditions of temperature, pressure, and chemical composition. When confronted with an object that formed under completely different conditions, these models fail to provide accurate predictions. This situation is reminiscent of other cases in astronomy, where the discovery of new types of objects forced revisions to existing theoretical frameworks. The discovery of pulsars, quasars, and exoplanets all required substantial modifications to our understanding of stellar and planetary physics. 3I/Atlas may represent a similar paradigm shift for our understanding of small body physics and planetary system formation processes. The study of 3I/Atlas is also revealing new insights into the diversity of planetary system formation outcomes. If objects with such extreme properties can form around other stars, It suggests that the range of possible planetary system architectures and compositions is much broader than previously thought. This has implications not only for cometary science, but also for our understanding of planetary formation processes and the potential habitability of exoplanetary systems. Fact 23. The October Mars Encounter. On October 3, 2025, 3I/Atlas will pass within 29 million kilometers of Mars. That's closer than Mars ever gets to Earth. This proximity offers an unprecedented opportunity for the various spacecraft orbiting the red planet to observe an interstellar object up close. The European Space Agency's Mars Express and ExoMars Trace Gas Orbiter are already preparing their cameras for this historic flyby. The Mars encounter represents one of the most favorable observational geometries we've ever had for studying an interstellar object. The closest approach distance of 29 million kilometers may sound large, but in astronomical terms, this is remarkably close. For comparison, Mars and Earth approach each other to minimum distances of about 55 million kilometers during favorable oppositions, and even then, only every 26 months. From Mars's perspective, 3I/Atlas will appear significantly brighter than it does from Earth due to the closer viewing distance. The inverse square law dictates that brightness increases with the square of decreasing distance, so the roughly tenfold closer approach from Mars compared to Earth will make the comet appear about 100 times brighter to Mars-based observers. This dramatic brightness increase will enable much more detailed observations than are possible from Earth-based telescopes. The European Space Agency has confirmed that both Mars Express and the ExoMars Trace Gas Orbiter will attempt to observe 3I/Atlas during its closest approach. Mars Express, which has been orbiting Mars since 2003, is the high-resolution stereo camera, HRSC, that could potentially capture detailed images of the interstellar visitor. The ExoMars Trace Gas Orbiter, which arrived at Mars in 2016, is equipped with the Color and Stereo Surface Imaging System, CAS-SIS, that could provide high-resolution color images. NASA's Mars Reconnaissance Orbiter, with its powerful HiRISI, high-resolution imaging science experiment camera, presents perhaps the most exciting opportunity for close-up imaging. HiRISI is capable of resolving features as small as 30 centimeters on the Martian surface from orbital distances of 250, 300 kilometers. While 3I/Atlas will be much farther away, the camera's exceptional resolution could still provide unprecedented detail about the comet's coma structure and potentially even constraints on the nucleus size. The observational geometry of the Mars encounter also offers unique scientific opportunities. Mars-based observers will see 3Y/Atlas from a different angle than Earth-based telescopes, potentially revealing different aspects of the comet's coma and tail structure. The three-dimensional information obtained by combining Earth and Mars observations could provide insights into the true spatial distribution of gas and dust around the nucleus. The timing of the Mars encounter is particularly fortuitous because it occurs just before 3I/Atlas reaches perihelion. At this point in its approach, the comet should be becoming increasingly active as solar heating intensifies, potentially displaying its most spectacular activity levels. The Mars-based observations could capture 3I/Atlas at a crucial phase of its evolution, providing data that will be impossible to obtain once the comet disappears behind the Sun from Earth's perspective. The Mars encounter also presents opportunities for coordinated observations across multiple wavelengths and instrument types. While imaging cameras provide visual information about coma structure and brightness distribution, some Mars orbiters also carry spectrometers that could potentially detect spectral signatures from 3I/Atlas's outgassing. The combination of imaging and spectroscopic data from close range could provide unprecedented insights into the comet's composition. Close range could provide unprecedented insights into the comet's composition and activity processes. From a technical perspective, observing a rapidly moving interstellar object from Mars' orbit presents significant challenges. The spacecraft must be precisely oriented to track 3Y/Atlas across the sky while maintaining stable pointing for image acquisition. The orbital mechanics of the Mars-based spacecraft add additional complexity, as their own motion around Mars must be accounted for when calculating pointing directions and exposure timing. The data transmission challenges are also substantial. Mars orbiters typically communicate with Earth through NASA's Deep Space Network, or ESA's equivalent facilities, but the data volumes generated by detailed observations of 3I/Atlas could strain these communication links. Priority must be given to the most scientifically valuable observations, and data compression techniques may be necessary to maximize the information return within available bandwidth constraints. The Mars Encounter observations will also provide valuable experience for planning future missions to interstellar objects. The techniques developed for tracking and observing 3I/Atlas from Mars orbit could inform the design of dedicated interstellar object rendezvous missions, should such opportunities arise in the future. Fact 24. Hidden during its moment of glory. Here's cosmic irony at its finest when 3I/Atlas reaches its closest approach to the Sun on October 29, 2025. It will be completely hidden from Earth's view. The comet and Earth will be on opposite sides of the Sun, meaning that during what could be its most spectacular display, we'll be unable to see it from our planet. It's nature's way of keeping some secrets to herself. Solar conjunction events are among the most frustrating phenomena in observational astronomy. Just when an object reaches its most active or interesting phase, it becomes impossible to observe because it appears too close to the Sun in Earth's sky. The brilliant solar disk completely overwhelms any signal from nearby celestial objects, creating an observational dead zone that can last for weeks or months depending on the object's orbital geometry. For 3I/Atlas, the solar conjunction occurs at the worst possible time from a scientific perspective. Perihelion represents the moment when solar heating reaches its maximum intensity, triggering the highest levels of outgassing and cometary activity. This is typically when comets develop their most spectacular tails, display their brightest comas, and provide the most detailed information about their nuclear composition, as subsurface materials are exposed to direct solar radiation. The timing of the conjunction is particularly cruel because it occurs during the brief window when 3I/Atlas its one and only passage through the inner solar system. Unlike periodic comets that return regularly and can be studied during multiple apparitions, this interstellar visitor offers only a single opportunity for detailed observation. The loss of the perihelion period represents an irreplaceable gap in our scientific understanding of this remarkable object. However, the solar conjunction period is not entirely without observational opportunities. Specialized solar observation spacecraft, designed to study the Sun and its immediate environment, might be able to detect 3I/Atlas, even when it's invisible from Earth. The Solar and Heliospheric Observatory, SOHO, positioned at the L1 Lagrange point between Earth and the Sun, carries coronagraphs that block out the solar disk and can sometimes detect comets passing through the inner solar system. NASA's Parker Solar Probe, which makes close approaches to the Sun as part of its mission to study the solar wind and corona, represents another potential observational opportunity during the conjunction period. If the timing and geometry are favorable, Parker Solar Probe might be able to observe 3I/Atlas from a unique vantage point close to the Sun, providing data that would be impossible to obtain from any other location. The European Space Agency's Solar Orbiter mission could also potentially contribute observations during the conjunction period, depending on its orbital position and instrument capabilities. These solar physics missions carry specialized instruments designed to operate in the intense radiation environment near the Sun, potentially allowing them to detect and track objects that are invisible from Earth-based observatories. The conjunction period also provides an opportunity to test theoretical models of cometary behavior under extreme solar heating conditions. While we cannot directly observe 3I/Atlas during perihelion, we can monitor its behavior before and after the conjunction to see how the intense solar heating affects its subsequent evolution. Changes in brightness, coma structure, or outgassing could provide indirect evidence of what occurred during the hidden perihelion phase. Ground-based radio telescopes might also provide limited observational capabilities during the conjunction period. Radio waves can penetrate the solar interference that blocks optical observations, potentially allowing detection of molecular emission lines from 3I/Atlas's coma, even when the comet is too close to the Sun for optical observation. However, the technical challenges of such observations are substantial, and the scientific return is likely to be limited compared to direct optical and infrared observations. The conjunction period highlights the importance of international coordination in observational astronomy. With Earth-based telescopes unable to track 3I/Atlas, the scientific community must rely on whatever space-based assets happen to be favorably positioned during this crucial period. The coordination of observations between different space agencies and missions becomes critical for maintaining observational continuity. The experience of losing 3I/Atlas during its most active phase also informs planning for future interstellar object discoveries. Early warning systems and rapid response capabilities become even more important when dealing with objects that have such compressed observational windows. The ability to mobilize observational resources quickly and coordinate international efforts could make the difference between comprehensive scientific characterization and missed opportunities. Fact 25. The December reappearance. After its hidden solar encounter, 3I/Atlas will emerge from behind the Sun and become visible from Earth again in early December 2025. By this time, it will be at its closest approach to our planet, about 270 million kilometers away. While this might sound far, it's actually relatively close in astronomical terms, about 1.8 times the distance from Earth to the Sun. The post-perihelion reappearance of 3I/Atlas represents one of the most anticipated astronomical events of late 2025. After weeks of being hidden behind the solar glare, the comet's emergence will reveal how it has been transformed by its close encounter with the Sun. The intense solar heating during perihelion could have triggered dramatic changes in the comet's activity level, coma structure, and overall appearance. The December observing geometry is particularly favorable because 3I/Atlas will be approaching its minimum distance from Earth, while also being positioned in the pre-dawn sky, where it can be observed during the darkest hours. This combination of proximity and favorable sky position could provide the best ground-based observing conditions for the entire apparition of this interstellar visitor. The closest approach distance of 270 million kilometers, while still vast by terrestrial standards, represents a remarkable opportunity in the context of interstellar object studies. This is much closer than either Oumuamua or 2I/Borisov approached Earth, providing an opportunity for much more detailed observations than were possible for the previous interstellar visitors. From an observational perspective, the post-perihelion period offers unique scientific opportunities. 3I/Atlas will have experienced maximum solar heating and may display the full range of its cometary activity. The comet might have developed multiple tails, extensive coma structures, or other phenomena that were not visible during its inbound approach when it was farther from the Sun and less active. The post-perihelion observations will also reveal how the extreme CO2 dominance of 3Wa/Atlas affects its response to intense solar heating. Different volatile materials respond differently to thermal input, and the unusual chemistry of this interstellar visitor could produce activity patterns that differ significantly from those observed in solar system comets. However, the December reappearance also brings challenges. Post-perihelion comets typically begin fading as they recede from the Sun, and the rate of this fading depends on the comet's volatile content and internal structure. If 3I/Atlas has limited volatile reserves or develops a protective crust during its fade rapidly, providing only a brief window for detailed post-perihelion observations. The December observing window also coincides with winter in Earth's northern hemisphere, when many major observatories experience reduced observing efficiency due to weather conditions. Coordinating observations between northern and southern hemisphere facilities becomes crucial for maximizing the scientific return during this critical period. Amateur astronomers around the world are also preparing for the December reappearance, hoping that 3I/Atlas might become bright enough to observe with modest telescopes. While the comet is unlikely to become a naked-eye object, it might reach brightness levels that make it accessible to dedicated amateur observers with appropriate equipment and dark sky sights. The post-perihelion period also offers opportunities for coordinated observations between ground-based and space-based facilities. The James Webb Space Telescope, Hubble Space Telescope, and other major space observatories will likely continue their monitoring campaigns, while ground-based facilities can provide complementary observations at different wavelengths and with different temporal coverage. The December observations will also provide crucial data for understanding the long-term evolution of 3Wa/Atlas as it begins its journey back to interstellar space. The rate at which the comet fades, the evolution of its spectral signatures, and changes in its coma structure will all provide insights into its physical properties and the effects of its solar encounter. Fact 26. A date with Jupiter. The cosmic choreography doesn't end with Mars and Earth. On March 16th, 2026, 3I/Atlas will pass within 53.6 million kilometers of Jupiter, close enough that some ambitious scientists have proposed using NASA's Juno spacecraft to intercept the interstellar visitor. This would require a complex orbital maneuver, but it could provide humanity's first close-up images of an object from another star system. The Jupiter encounter represents the final major planetary interaction for 3I/Atlas during its passage through our solar system. By March 2026, the comet will be well past perihelion and beginning its long journey back to interstellar space, but it will still be close enough to the Sun to potentially maintain some level of activity that could be detected by close-range observations. The proposal to redirect NASA's Juno spacecraft to intercept 3I/Atlas has captured the imagination of both scientists and the public. Juno, which has been orbiting Jupiter since July 2016, was originally scheduled to end its mission by plunging into Jupiter's atmosphere to avoid any risk of contaminating the potentially habitable moons Europa and Ganymede. However, the opportunity to encounter an interstellar object has led to serious consideration of extending and redirecting the mission. The technical challenges of such a mission are substantial, but not insurmountable. According to detailed trajectory analysis conducted by Harvard University's Abraham Loeb and colleagues, the required maneuver would involve applying a total velocity change of approximately 2.675 kilometers per second, executed in two phases. The first phase would lower Juno's orbital altitude around Jupiter, and the second would use a Jupiter gravity assist maneuver to redirect the spacecraft towards the intercept trajectory. The timing of this maneuver is critical and unforgiving. The analysis suggests that the necessary thrust would need to be applied on September 9, 2025, just 8 days before Juno's originally planned mission termination. This narrow timing window reflects the precise orbital mechanics required to achieve the intercept, with very little margin for error or delay. If successful, the Juno intercept would provide unprecedented scientific opportunities. The spacecraft carries a comprehensive suite of instruments, including a near-infrared spectrometer, magnetometer, microwave radiometer, gravity science instrument, energetic particle detector, radio and plasma wave sensor, UV spectrograph, and visible light camera. This instrument complement would allow detailed characterization of 3 I/8LAS from multiple perspectives simultaneously. The close-range observations possible with a spacecraft encounter would address many of the fundamental questions about 3 I/Atlas that cannot be answered from ground-based telescopes. Direct imaging could finally reveal the size, shape, and surface properties of the nucleus, while close-range spectroscopy could provide definitive measurements of the comet's composition and outgassing processes. The gravitational field measurements possible with Juno's precision tracking could provide the first direct measurement of an interstellar object's mass and density. This information would be crucial for understanding the internal structure and formation history of 3 I/Atlas, providing constraints that are impossible to obtain from remote observations. However, the proposed mission also carries significant risks and uncertainties. The trajectory calculations are based on current predictions of 3 I/Atlas's orbit, but cometary outgassing can create non-gravitational forces that alter an object's trajectory in unpredictable ways. If 3 I/Atlas's path changes significantly due to cometary activity, the intercept could fail despite perfect execution of the planned maneuvers. The technical readiness of the Juno spacecraft for such an extended mission is another consideration. The spacecraft has been operating in Jupiter's harsh radiation environment for nearly a decade, and its systems are approaching or exceeding their design lifetimes. The additional stress of an extended mission and the complex maneuvers required for the intercept could push the aging spacecraft beyond its operational limits. The fuel requirements for the intercept maneuver are also substantial. Juno would need to use virtually all of its remaining propellant to achieve the necessary velocity changes, leaving no margin for trajectory corrections or extended observations once the intercept is achieved. This all-or-nothing approach reflects the unique and unrepeatable nature of the opportunity. The scientific value of a successful intercept would be immense, but the mission would also carry important symbolic significance. It would represent humanity's first intentional close encounter with a visitor from another star system, marking a historic milestone in our exploration of the cosmos. The images and data returned from such an encounter would provide material for scientific study for decades to come. Fact 27. The Juno mission possibility. The proposal to redirect Juno toward 3 I/Atlas reads like science fiction. It would require applying a thrust of 2.675 kilometers per second on September 9th, 2025, just 8 days before Juno's originally planned termination. This maneuver would use Jupiter's gravity in what's called an O-berth maneuver, potentially bringing the spacecraft within close range of 3 I/Atlas on March 14th, 2026. The O-berth maneuver is one of the most elegant concepts in orbital mechanics, allowing spacecraft to achieve maximum efficiency in velocity changes by performing engine burns at the point of closest approach to a massive body. When a spacecraft is deep in a gravitational well, the same amount of thrust produces a larger change in orbital energy than would be achieved in free space. This effect can be used to dramatically amplify the effectiveness of spacecraft propulsion systems. In the case of the proposed Juno intercept, the spacecraft would use its main engine to perform a deep periapsis burn while passing close to Jupiter. The intense gravitational field at this location would amplify the effect of the propulsive maneuver, allowing Juno to achieve the large velocity change necessary to escape Jupiter's gravitational influence and pursue 3-Atlas. The precise timing requirements for this maneuver reflect the unforgiving nature of orbital mechanics. The intercept trajectory has been calculated based on the predicted positions of both Juno and 3-Atlas on specific dates, accounting for the complex gravitational influences of the Sun, Jupiter, and other planets. Even small delays in executing the maneuver could result in mission failure, as the rapidly changing orbital geometries would make the intercept impossible. The two-phase nature of the proposed maneuver adds additional complexity to the mission plan. The first phase would involve lowering Juno's orbit around Jupiter to set up the optimal geometry for the Oberth maneuver. This preparatory burn would need to be executed with high precision to ensure that the spacecraft is in the correct position for the second, more critical burn that would send it toward 3-Atlas. The navigation challenges for such a mission are unprecedented in interplanetary spaceflight. Unlike typical planetary missions where the target is a large, predictable body with a well-known orbit, 3-Atlas is a small, potentially active comet whose trajectory could be altered by non-gravitational forces from outgassing. The navigation team would need to continuously monitor the comet's position and update the spacecraft's trajectory to maintain intercept accuracy. The communication challenges during such a mission would also be substantial. As Juno travels from Jupiter toward the intercept point, it would be moving rapidly through the solar system with constantly changing geometry relative to Earth. Maintaining reliable communication links would require careful planning of antenna pointing and data transmission schedules, particularly during critical maneuver phases when precise navigation updates are essential. The scientific planning for a Juno intercept mission would need to balance multiple competing objectives within severe constraints. The spacecraft's instrument suite was designed for studying Jupiter and its magnetosphere, not for close-range comet observations. Adapting the observation sequences to maximize scientific return from an interstellar object encounter would require extensive reprogramming and testing of spacecraft systems. The data storage and transmission requirements for such a mission would be enormous. High-resolution images and spectra of 3-Atlas would generate data volumes that far exceed Juno's original mission requirements. The spacecraft would need to prioritize the most scientifically valuable observations and potentially compress data to fit within available storage and transmission capabilities. The risk assessment for the proposed mission reveals the audacious nature of the undertaking. The spacecraft would be operating well beyond its design lifetime, executing complex maneuvers that were never part of the original mission plan, and attempting to intercept a small, unpredictable target billions of kilometers from Earth. The probability of complete success is difficult to estimate, but even partial success would provide invaluable scientific data. Fact 28. Arsenal of instruments ready. NASA has mobilized an unprecedented array of instruments to study 3-Atlas. The list reads like a roll call of humanity's greatest space telescopes: Hubble, James Webb, the Transiting Exoplanet Survey Satellite, the Swift Observatory, SPHEREX, and even Mars rovers like Perseverance and Curiosity. Never before have so many advanced instruments been focused on a single interstellar object. The coordination of this observational campaign represents one of the most complex international scientific collaborations ever undertaken. Each instrument brings unique capabilities and operates within specific constraints, requiring careful scheduling to ensure optimal coverage throughout three I/Atlas's passage through the solar system. The timing must account for each observatory's orbital mechanics, operational schedules, and technical limitations. The Hubble Space Telescope contributes unparalleled high-resolution imaging capabilities in visible and near-infrared wavelengths. Its ability to track moving objects while maintaining sharp image quality makes it ideal for monitoring changes in 3I/Atlas's Comet structure and searching for evidence of the elusive nucleus. The telescope's long operational history and well-calibrated instruments also provide a stable reference point for comparing observations with other facilities. The James Webb Space Telescope brings revolutionary infrared capabilities to the study of 3I/Atlas. Its unprecedented sensitivity and spectral resolution in the near and mid-infrared allow detailed chemical analysis of the comet's outgassing, revealing molecular species and isotopic ratios that are impossible to detect from ground-based observatories. Webb's observations have already provided the crucial data, revealing the extreme CO2/H2O ratio that makes this object so unusual. The Transiting Exoplanet Survey satellite, despite being designed for a completely different scientific purpose, has provided unique longitudinal data on 3I/Atlas's activity evolution. TESS's wide-field imaging and continuous monitoring capabilities allow detection of subtle brightness changes and activity patterns that would be missed by targeted observations with other instruments. The Swift Observatory contributes crucial capabilities in ultraviolet and X-ray wavelengths that are inaccessible from ground-based telescopes. These high-energy observations can reveal information about the interaction between 3I/Atlas and the solar wind, potentially detecting X-ray emission from charge exchange processes as solar wind ions collide with neutral atoms in the comet's coma. SPHEREX, NASA's newest space telescope, provides all-sky spectroscopic surveys in near-infrared wavelengths that are perfect for mapping the extended CO2 coma of 3I/Atlas. Its wide-field capabilities allow simultaneous observation of the comet and surrounding regions, providing context for understanding how the object interacts with the interplanetary environment. Ground-based observatories around the world have also contributed to the observational campaign. Major facilities like the European Southern Observatory's Very Large Telescope, the Keck Observatory in Hawaii, the Subaru Telescope, and the Atacama Large Millimeter Array have all dedicated significant observing time to 3I/Atlas studies. This international cooperation ensures continuous coverage as Earth's rotation and orbital motion change the visibility of the comet from different locations. Even the Mars rovers Perseverance and Curiosity have been enlisted in the observational campaign, though their contributions are necessarily limited by their surface-based locations and instrument capabilities. These rovers can provide unique perspectives on 3I/Atlas during its October 2025 close approach to Mars, potentially capturing images of the comet from the Martian surface that would be impossible to obtain from any other vantage point. The data integration challenges for such a diverse observational campaign are substantial. Each instrument operates at different wavelengths with different sensitivities and resolution capabilities. Combining observations from multiple facilities requires careful calibration and cross-validation to ensure that the integrated dataset provides a coherent picture of 3I/Atlas's properties and behavior. The scheduling coordination for this multi-observatory campaign requires unprecedented levels of international cooperation and communication. Observing proposals must be submitted to multiple facilities simultaneously, with careful attention to overlap and complementarity between different observations. The rapid changes in 3I/Atlas's position and activity level require flexible scheduling that can adapt to new developments, and optimize scientific return. Fact 29. The TESS time machine. NASA's TESS satellite actually captured images of 3I/Atlas back in May 2025, nearly 2 months before its official discovery. However, because TESS is designed to monitor stars for exoplanet transits, not fast-moving comets, special image stacking techniques were needed to reveal the object. This early detection shows that 3I/Atlas was already active when it was beyond Jupiter's orbit. The retroactive discovery of 3I/Atlas in TESS data highlights both the power and limitations of automated astronomical surveys. TESS was designed with sophisticated algorithms to detect the periodic dimming of stars caused by transiting exoplanets, but these same algorithms are not optimized to recognize the signatures of rapidly moving objects like comets or asteroids. The image stacking technique used to reveal 3I/Atlas in the TESS data involves a process called shift and stack analysis. Astronomers must first calculate the predicted motion of the comet across the TESS images based on its known orbital parameters, then shift and add multiple images to track the object's movement. This technique can reveal faint moving objects that would be invisible in individual images. The May 2025 TESS observations show 3I/Atlas when it was approximately 6 astronomical units from the Sun, well beyond the orbit of Jupiter. At this distance, most solar system comets remain completely dormant, with their volatile materials locked in solid form and no detectable activity. The fact that TESS could detect a coma around 3I/Atlas at such a great distance demonstrates both the unusual nature of this object and the remarkable sensitivity of modern astronomical instruments. The early activity detected by TESS provides crucial constraints on the volatile composition and thermal properties of 3I/Atlas. For the comet to show detectable outgassing at 6 AU, it must contain materials that sublime at much lower temperatures than the water ice that dominates most solar system comets. This early evidence of unusual composition foreshadowed the later discovery of the extreme CO2 dominance revealed by infrared spectroscopy. The TESS detection also demonstrates the value of archival astronomical data. The satellite continuously monitors large portions of the sky, creating an invaluable archive of time-domain astronomical data. Objects like 3I/Atlas can be discovered retroactively by searching these archives once their orbital parameters are known, effectively extending the observational baseline and providing additional scientific data. The technical challenges of extracting comet signals from TESS data designed for stellar monitoring are substantial. The satellite's cameras and data processing systems are optimized for detecting subtle brightness variations in stationary stars, not for tracking rapidly moving objects against changing stellar backgrounds. The successful extraction of 3I/Atlas data required innovative analysis techniques and careful attention to instrumental effects. The May observations from TESS reveal that 3I/Atlas had already developed a detectable coma with a radius of approximately 23 kilometers when it was still very far from the Sun. This early coma development suggests either an unusually high abundance of volatile materials or surface properties that facilitate easy outgassing even under minimal solar heating. The temporal evolution of 3I/Atlas's activity, as revealed by combining TESS observations with later ground-based and space-based monitoring, provides insights into how the comet responds to increasing solar heating. The smooth increase in activity level from May through July 2025 suggests that the outgassing processes follow predictable thermal models, despite the unusual chemical composition. The TESS observations also provide important calibration data for interpreting later, more detailed observations of 3I/Atlas. By establishing the comet's behavior during its early approach phase, The test data help astronomers understand how the object's activity has evolved as it continues toward perihelion. Fact 30. Abnormal activity patterns. The early TESS observations revealed that 3I/Atlas was showing cometary activity at a distance of about 6 astronomical units from the Sun, much farther than typical comets begin to show activity. Even more unusual, it was already displaying a coma with a radius of 23 kilometers around its nucleus, suggesting extremely volatile materials that sublime at very low temperatures. The 6 AU activity onset distance places 3I/Atlas in a very unusual category of comets. In our solar system, only a handful of comets have been observed to show activity at such great distances, and these are typically objects with unusual compositions or structures. The famous comet 29P/Schwarzmann-Wachmann is one of the few solar system comets that shows persistent activity at similar distances, but its behavior is attributed to specific orbital characteristics and composition that differ significantly from typical comets. The 23-kilometer coma radius detected by TESS represents a substantial envelope of gas and dust around the nucleus, especially considering the minimal solar heating available at 6 AU. The production of such an extensive coma requires significant outgassing rates, which in turn demands either abundant volatile materials or highly efficient sublimation processes. The temperature conditions at 6 AU are crucial for understanding the unusual early activity of 3I/Atlas. At this distance, the equilibrium temperature of a rapidly rotating black body would be approximately 120–130 Kelvin, depending on the exact solar distance and the object's thermal properties. Most volatile materials common in solar system comets, including water ice, remain stable at these temperatures. However, highly volatile materials like carbon monoxide, nitrogen, or exotic ices could potentially sublime at these low temperatures. The early activity of 3I/Atlas provides strong evidence that its composition includes substantial amounts of such highly volatile materials, consistent with the later discovery of its unusual chemical signatures. The early onset of activity also has implications for understanding the internal structure of 3I/Atlas. Most solar system comets develop protective crusts of non-volatile material over multiple passages near the Sun, and these crusts can inhibit outgassing until they are breached by thermal stress or other mechanisms. As a first-time visitor to the inner solar system, 3I/Atlas likely has a pristine surface that allows direct access of subsurface volatiles to solar heating. The thermal modeling of 3I/Atlas's early activity suggests that its surface properties differ significantly from those of typical solar system comets. The efficient outgassing at low temperatures could indicate a highly porous structure that allows easy escape of sublimated gases, or it could reflect a composition dominated by materials with lower sublimation temperatures than water ice. The spatial distribution of the early coma also provides clues about the activity patterns on the nucleus. A symmetric 23-kilometer radius coma suggests relatively uniform outgassing across the nucleus surface, though this could also result from the low activity levels and large viewing distance that make it difficult to resolve asymmetric structures. The temporal stability of the early activity, as revealed by multiple TESS observations over several weeks, suggests that the outgassing processes were relatively steady during this phase. This contrasts with some comets that show sporadic or variable activity patterns, particularly during their initial activation phases. The comparison between 3I/Atlas's early activity and that of previously studied interstellar objects reveals significant differences. 2I/Borisov, the only other well-studied interstellar comet, showed more conventional activity patterns with onset closer to the Sun and chemical compositions more similar to solar system comets. The extreme early activity of 3.1/Atlas reinforces its status as a truly unusual object. Fact 31. The fading race. Astronomers are in a race against time and distance. As 3.1/Atlas moves away from the Sun after its October perihelion, it will gradually fade from view. The window for detailed observations is rapidly closing, making every telescope session precious. By mid-2026, the comet will be too faint for all but the most powerful instruments to detect. The observational timeline for 3.1/Atlas is dictated by the fundamental physics of cometary brightness evolution. As the comet recedes from the Sun after perihelion, it receives less solar heating, leading to reduced outgassing and dimmer coma brightness. The rate of this fading depends on several factors, including the comet's volatile content, nuclear size, and the efficiency of its outgassing processes. Theoretical models of cometary brightness evolution typically predict that brightness should decrease roughly proportionally to the inverse fourth power of solar distance for dust-dominated comets, or somewhat less steeply for gas-dominated objects. However, the unusual composition of 3.1/Atlas makes it difficult to apply standard brightness evolution models with confidence. The current observational cadence represents an intensive effort to maximize data collection. Major observatories are scheduling observations as frequently as possible, balancing the need for continuous monitoring against the limitations of telescope availability and observing conditions. Weather, instrumental maintenance, and competing scientific priorities all constrain the actual amount of observing time available. The fading timeline has important implications for different types of observations. High-resolution imaging and detailed spectroscopy require substantial amounts of collected light, making them increasingly difficult as the comet fades. Broadband photometry and basic position measurements can continue with fainter objects, but the most scientifically valuable observations will become impossible as 3.1/Atlas dims below critical brightness thresholds. The distance factor compounds the brightness problem. As 3.1/Atlas moves away from the Sun, it also increases its distance from Earth, creating a double effect on observed brightness. The comet receives less solar energy to drive outgassing, while simultaneously appearing fainter due to increased viewing distance. Different wavelengths fade at different rates, creating additional observational challenges. Visible light observations, which depend primarily on scattered sunlight from dust particles, typically fade more rapidly than infrared observations that can detect thermal emission and molecular transitions. This means that the observational capabilities for different types of scientific measurements will be lost at different rates. The international coordination of observations becomes even more critical as the observational window narrows. With limited time remaining, duplicated observations between different facilities represent lost opportunities for gathering unique data. The astronomical community has developed informal protocols for sharing observing plans and coordinating complementary observations to maximize return. Amateur astronomers face particular challenges in the fading race. While professional observatories have access to large telescopes and sensitive detectors, amateur equipment is limited to brighter objects. The window for amateur observations of 3.1/Atlas may already be closing or may never have opened, depending on how bright the comet becomes during its most active phase. The data analysis timeline also creates pressure in the fading race. As new observations are obtained, they must be processed and analyzed quickly enough to inform planning for subsequent observations. The rapid pace of data collection leaves little time for the careful analysis that typically characterizes astronomical research, requiring real-time decision-making based on preliminary results. The psychological pressure of the fading race affects everyone involved in 3 I/8less observations. Unlike typical astronomical targets that can be studied for years or decades, this interstellar visitor presents a once-in-a-lifetime opportunity that is slipping away with each passing day. The knowledge that any missed observations represent permanently lost scientific opportunities adds urgency to every aspect of the observational campaign. Fact 32. Retrograde revolution. The fact that 3 I/Atlas moves in retrograde motion opposite to the planets tells us something profound about its journey. Unlike the previous interstellar visitors, Oumuamua and 2I/Borisov, which approached more head-on relative to the solar system's motion, 3 I/Atlas came at us sideways, suggesting it originated from a completely different region of the galaxy. The retrograde orbital motion of 3 I/Atlas provides crucial information about its galactic trajectory and origin. In the context of galactic dynamics, objects that approach our solar system in retrograde fashion have typically experienced different gravitational influences and follow different paths through the galaxy compared to objects with prograde motion. The comparison with previous interstellar visitors is particularly illuminating. Oumuamua had an orbital inclination of about 122 degrees, indicating retrograde motion, but not as extreme as 3 I/Atlas. 2 I/Borisov showed an inclination of about 44 degrees, indicating prograde motion similar to solar system objects. The 175-degree inclination of 3 I/Atlas represents the most extreme retrograde motion observed in any interstellar object. The nearly polar orbit of 3 I/Atlas, combined with its high velocity, suggests that it has experienced significant gravitational scattering during its journey through the galaxy. Objects that maintain orbits close to the galactic plane typically show less extreme orbital inclinations, while objects that have been scattered into highly inclined trajectories often show evidence of interactions with massive perturbing influences. The retrograde motion also affects the observational timeline and encounter geometry for studying 3 I/Atlas. Because the comet is moving opposite to Earth's orbital motion around the Sun, the relative velocity between our planet and the interstellar visitor is higher than it would be for a prograde object. This increases the apparent angular motion of the comet across the sky and compresses the observational window. From a statistical perspective, the retrograde motion of 3 I/Atlas contributes to our understanding of the orbital distribution of interstellar objects. If such objects were distributed randomly in velocity space, we would expect to see roughly equal numbers with prograde and retrograde motion. The fact that we've now observed objects with a wide range of inclinations suggests that interstellar objects do indeed sample diverse galactic populations and trajectories. The extreme retrograde motion also has implications for understanding the formation and ejection mechanisms that create interstellar objects. In most planetary system formation scenarios, objects are ejected with velocities and trajectories that reflect the orbital architecture of their parent systems. The highly inclined retrograde trajectory of 3 I/8less suggests ejection processes that imparted significant angular momentum relative to the galactic plane. The galactic context of the retrograde motion provides additional insights. Objects that spend significant time in the galactic halo or thick disk often develop high inclination orbits relative to the main galactic plane. The trajectory of 3 I/Atlas is consistent with an origin in one of these older, more scattered stellar populations, supporting other evidence for its ancient age and unusual formation environment. The retrograde motion also affects how 3I/Atlas interacts with the heliosphere and solar wind. Objects approaching the solar system in retrograde fashion encounter the solar wind and interplanetary magnetic field from different angles than prograde objects, potentially creating different patterns of cometary activity and tail development. The navigation and prediction challenges created by retrograde motion are also significant. Small errors in position measurements or orbital calculations can lead to larger uncertainties in predicting future positions for retrograde objects, making observation planning and potential spacecraft missions more challenging. Fact 33. The thick disk theory. Computer simulations of 3I/Atlas's trajectory through the galaxy suggest it spent most of its existence in the Milky Way's thick disk, a region populated by stars that are typically 8 to 12 billion years old. If true, this makes 3I/Atlas a messenger from the galaxy's ancient past, carrying materials that formed when the universe was less than half its current age. The thick disk of our galaxy represents one of the oldest stellar components accessible to detailed study, and 3I/Atlas potentially provides our first direct sample of material from this ancient population. The thick disk formed during the early assembly of our galaxy, when star formation rates were higher, galaxy mergers were more common, and the chemical composition of interstellar gas differed significantly from today's conditions. The computer simulations that trace 3I/Atlas backward through galactic time involve complex calculations that account for the changing gravitational field of the galaxy, the motion of spiral arms, encounters with molecular clouds, and interactions with other stellar systems. These simulations can follow the object's trajectory for millions or billions of years, though uncertainties increase rapidly as the integration time extends further into the past. The thick disk origin theory helps explain several of the unusual properties observed in 3I/Atlas. Stars in the thick disk typically have lower metallicities, lower abundances of elements heavier than hydrogen and helium compared to younger stellar populations. This difference in heavy element abundance could affect the chemistry of planetary formation and comet composition in ways that explain the unusual CO2/H2O ratio observed in 3I/Atlas. The age implications of a thick disk origin are staggering. If 3I/Atlas formed around a thick disk star 1012 would have existed for more than twice the age of our solar system. During this time, it would have witnessed multiple galactic processes, including spiral arm passages, encounters with star-forming regions, and the gradual chemical evolution of the galaxy as successive generations of stars enriched the interstellar medium. The preservation of such an ancient object through billions of years of galactic evolution is remarkable and provides insights into the stability of small bodies in interstellar space. The fact that 3I/Atlas has retained its structural integrity and much of its volatile content suggests that interstellar space is less hostile to small objects than some models predict. The thick disk theory also has implications for understanding the population of interstellar objects in our galaxy. If ancient stellar populations can contribute long-lived wandering objects like 3I/Atlas, the total population of interstellar objects might be much larger and more diverse than estimates based solely on younger stellar populations. The chemical signatures expected from thick disk formation environments include not only different heavy element abundances, but also different isotopic ratios that reflect the nuclear processing history of earlier stellar generations. Detailed spectroscopic analysis of 3I/Atlas might reveal isotopic signatures that confirm its ancient origin and provide direct measurements of galactic chemical evolution. The thick disk origin also suggests that 3I/Atlas may have experienced different radiation environments during its formation and early evolution. The early galaxy had higher rates of star formation and supernova explosions, creating more intense radiation fields and different chemical processing conditions than those present in the current galactic environment. The orbital characteristics that link 3Y/8 to the thick disk high velocity, large galactic scale height, and retrograde motion are also consistent with objects that have experienced significant gravitational scattering over long time periods. The accumulation of random velocity components through countless gravitational encounters could explain how an object originally formed in a more orderly stellar environment developed such extreme orbital characteristics. Fact 34. Chemical time capsule. The unusual chemistry of 3Y/Atlas, dominated by carbon dioxide rather than water, may preserve conditions from the early galaxy. In the ancient universe, stellar nuclear synthesis hadn't yet produced the heavier elements we see today. The high CO2 content might reflect formation around stars with different compositions than our Sun, or in regions with different temperature and radiation conditions. The concept of 3I/Atlas as a chemical time capsule represents one of the most exciting aspects of its discovery. Unlike distant galaxies or ancient stars that we can only study through their light, this object potentially carries actual material from the early universe that we can analyze in detail with our most sophisticated instruments. The carbon and oxygen chemistry preserved in 3I/Atlas reflects the nucleosynthetic history of its formation environment. In the early universe, the first generations of stars produced primarily light elements through nuclear fusion, while heavier elements were synthesized in smaller quantities. The ratio of carbon to oxygen and the specific isotopic signatures of these elements carry information about the stellar populations that existed when 3W/Atlas formed. The preservation of ancient chemical signatures over billions of years requires specific conditions that prevent significant alteration of the original composition. The cold environment of interstellar space, with temperatures only a few degrees above absolute zero, provides excellent preservation conditions for volatile materials. However, cosmic ray processing and other space weathering effects can gradually modify surface chemistry over long time periods. The dominance of carbon dioxide in 3I/Atlas might reflect formation in a protoplanetary disk with a different carbon to oxygen ratio than the material that formed our solar system. In oxygen-rich environments, carbon preferentially forms CO and CO2, while in carbon-rich environments, more complex organic molecules can form. The specific CO ratio influences which volatile species condense at different temperatures and distances from the parent star. The isotopic ratios preserved in 3I/Atlas could provide direct measurements of galactic chemical evolution over cosmic time. Different generations of stars produce characteristic isotopic signatures through their nuclear processing, and the ratios of isotopes like 12C/13C, 16O/18O, and others can reveal the stellar nucleosynthetic environment present when the comet formed. The chemical time capsule concept also extends to trace elements and molecular species that might be preserved in the nucleus of 3I/Atlas. Noble gases, in particular, are excellent tracers of formation conditions because they are chemically inert and preserve the isotopic signatures of their original incorporation into solid materials. The analysis of 3I/Atlas as a chemical time capsule requires extremely sensitive spectroscopic techniques that can detect and measure trace molecular species in the comet's coma. Each detected molecule provides a piece of the puzzle about formation conditions, though interpreting these signatures requires careful modeling of how materials sublimate and interact with solar radiation. The comparison between 3Y/Atlas's chemistry and that of solar system objects provides a unique opportunity to study the diversity of planetary formation environments across different stellar systems and epochs. The extreme differences observed suggest that planetary system formation processes can produce dramatically different outcomes depending on local conditions and stellar properties. The preservation of chemical signatures from the early galaxy also has implications for astrobiology and the distribution of organic molecules in space. Understanding how carbon chemistry evolved in different stellar environments provides context for evaluating the potential for life in ancient planetary systems and the molecular precursors available for biological processes. Fact 35. The size controversy. One of the biggest mysteries surrounding 3I/Atlas is its actual size. Early estimates suggested it could be up to 24 kilometers across, which would make it monumentally large for an interstellar object. However, Hubble observations suggest the nucleus might be much smaller, with most of the observed brightness coming from its enormous coma rather than reflected sunlight from the solid surface. The size determination problem illustrates one of the fundamental challenges in studying active comets. When a comet develops an extensive coma, the solid nucleus becomes completely overwhelmed by the much brighter gas and dust envelope surrounding it. Traditional methods for measuring asteroid sizes, which rely on the relationship between brightness and surface area, become unreliable when applied to active comets. The early size estimates of up to 24 kilometers in diameter were based on photometric observations that assumed typical reflectivity properties and standard relationships between brightness and size. However, these calculations did not account for the substantial contribution of coma emission to the total observed brightness. As more detailed observations became available, it became clear that much of the light from 3I/Atlas comes from its extensive atmosphere rather than the solid surface. The Hubble Space Telescope observations provide the highest resolution data available for constraining the nucleus size. But even these observations cannot directly resolve the solid body. Instead, astronomers must use sophisticated modeling techniques to separate potential nucleus contributions from the dominant coma emission. These models depend on assumptions about dust production rates, gas expansion velocities, and coma structure that introduce uncertainties into size estimates. The size controversy has important implications for understanding the total mass and gravitational binding energy of 3I/Atlas. A 24-kilometer diameter object would have roughly 1,000 times more volume than a 2.4-kilometer diameter object, representing dramatically different amounts of material and different formation requirements. Large interstellar objects should be much rarer than smaller ones, making their detection statistically unlikely. The brightness evolution of 3I/Atlas as it approaches and recedes from the Sun provides additional constraints on nucleus size. Objects with different sizes should show different patterns of brightness change depending on how their surface area and activity levels respond to changing solar heating. Monitoring these brightness changes can help distinguish between size-related effects and activity-related contributions to the total light output. The thermal properties inferred from the size estimates also affect our understanding of 3I/Atlas's response to solar heating. Larger objects have lower surface area to volume ratios, meaning they respond more slowly to changing thermal conditions. The rapid onset of activity observed in 3I/Atlas might favor smaller size estimates, as smaller objects can change temperature more quickly as solar heating increases. The size uncertainty also affects estimates of the volatile content and potential lifetime of 3I/Atlas's activity. A larger nucleus could sustain outgassing for longer periods and at higher rates, while a smaller nucleus might exhaust its volatile reserves more quickly. Understanding the true size is crucial for predicting how long the comet will remain active and observable. The statistical implications of the size estimates are also significant for understanding interstellar object populations. If 3I/Atlas is indeed very large, it suggests that our detection methods are biased towards the largest and brightest interstellar visitors, and that many smaller objects pass through our solar system undetected. Alternatively, smaller size estimates would be more consistent with theoretical predictions of interstellar object size distributions. The size controversy highlights the limitations of remote sensing techniques for characterizing small, active objects at large distances. Resolving this fundamental question about 3I/Atlas may require new observational techniques, longer baseline observations, or even close spacecraft encounters that can directly image the nucleus and measure its properties. Fact 36. Dust production rates. Despite its potentially large size, 3I/Atlas has surprisingly low dust production rates compared to what would be expected from a comet of its dimensions. This suggests either that it has a very inactive surface, possibly covered by a protective crust, or that its composition is fundamentally different from solar system comets, with less dust-producing material. The measurement of dust production rates in comets involves analyzing the brightness and spatial distribution of scattered sunlight from dust particles in the coma. Different dust particle sizes scatter light differently, and the total amount of scattered light provides information about the mass production rate of dust from the nucleus surface. For 3I/Atlas, the dust production rate estimates are complicated by the dominance of gas emission over dust scattering in the comet's brightness. The carbon dioxide-rich coma is largely transparent to visible light, making traditional dust analysis techniques less reliable. Most of the observed brightness appears to come from direct gas emission and fluorescence rather than dust scattering. The low dust production rates could indicate several different physical processes. One possibility is that 3I/Atlas has developed a protective crust of non-volatile material that inhibits the escape of dust particles while allowing gases to escape through cracks or porous regions. Such crusts are common in solar system comets that have made multiple approaches to the Sun. However, as a first-time visitor to the inner solar system, 3I/Atlas should not have had the opportunity to develop a protective crust through previous solar heating cycles. This suggests that the low dust production might reflect inherent properties of the nucleus composition or structure rather than evolutionary effects. An alternative explanation for the low dust production is that 3I/Atlas simply contains less solid dust material relative to volatile ices than typical solar system comets. The unusual formation environment that produced its extreme CO2/H2O ratio might also have resulted in different dust-to-ice ratios that favor gas production over dust emission. The particle size distribution of dust in 3I/Atlas's coma also provides information about dust production processes. Larger dust particles are more difficult to accelerate away from the nucleus by gas pressure, requiring higher gas production rates to achieve the same dust entrainment efficiency. The observed dust characteristics might reflect the gas dynamics in the unusual CO2-dominated environment around 3I/Atlas. The temporal evolution of dust production rates also provides insights into the internal structure and activity patterns of 3I/Atlas. Most solar system comets show variable dust production that correlates with rotation periods, surface heterogeneity, and seasonal effects as different regions become more or less illuminated. The monitoring of dust production changes in 3I/Atlas could reveal similar patterns or entirely new behaviors. The low dust production rates have practical implications for observing 3I/Atlas from Earth. Dust-poor comets typically appear fainter in visible light observations, making them more challenging targets for amateur astronomers and smaller telescopes. the scientific emphasis necessarily shifts toward infrared and spectroscopic observations that can detect gas emission rather than dust scattering. The comparison with other interstellar objects provides additional context for interpreting the dust production rates of 3I/Atlas. 2I/Borisov showed more conventional dust production patterns similar to solar system comets, while Oumuamua showed little evidence of significant outgassing or dust production. 3I/Atlas appears to represent an intermediate case with substantial gas production but limited dust emission. The dust production analysis also has implications for understanding the mechanical properties of the nucleus surface. Different surface materials and structures produce different dust liberation efficiencies under thermal stress. The low dust production might indicate that 3I/Atlas has a more coherent or consolidated surface structure compared to the loose, fragmented surfaces typical of many solar system comets. Fact 37. The carbonyl sulfide signature. Among the gases detected in 3I/Atlas's coma is carbonyl sulfide, OCS, a molecule that's relatively rare in solar system comets. On Earth, this compound is associated with industrial processes and volcanic emissions. Its presence in an interstellar comet provides clues about the chemical processes that occurred around ancient stars billions of years ago. The detection of carbonyl sulfide represents one of the most intriguing chemical discoveries in 3I/Atlas's spectrum. This molecule consists of carbon, oxygen, and sulfur arranged in a linear structure, and its presence requires specific formation conditions that are not common in typical solar system environments. The molecule has been detected in only a handful of solar system comets, making its identification in an interstellar object particularly significant. The formation pathways for carbonyl sulfide in astronomical environments involve complex chemical networks that require specific temperature and pressure conditions. In star-forming regions and protoplanetary disks, OCS can form through gas phase reaction between carbon monoxide and sulfur-bearing species, or through surface reactions on dust grains at low temperatures. The presence of OCS in 3I/Atlas suggests that such chemical pathways were active in its formation environment. The sulfur chemistry preserved in 3I/Atlas provides additional constraints on its formation conditions. Sulfur is less abundant than carbon or oxygen in most astronomical environments, but it plays important roles in the chemical networks that produce complex molecules. The incorporation of sulfur into stable molecular forms like OCS requires specific chemical conditions that differ from those needed to produce more common species like CO2 or H2O. The detection of carbonyl sulfide also has implications for understanding the thermal processing history of 3I/Atlas. OCS is a relatively fragile molecule that can be destroyed by intense radiation or high temperatures. Its preservation in detectable quantities suggests that the comet has not experienced extreme thermal processing during its billions of years of interstellar travel. The spectroscopic identification of OCS in 3I/Atlas required high-resolution infrared observations that can resolve the characteristic vibrational and rotational transitions of this molecule. The detection represents a significant technical achievement, given the low abundance of OCS compared to major species like CO2, and the challenging observational conditions imposed by the comet's faintness and rapid motion. The comparison of OCS abundance in 3I/Atlas with that observed in solar system comets provides insights into the diversity of chemical processing environments in different stellar systems. The relative abundances of different sulfur-bearing molecules can reveal information about temperature profiles, radiation fields, and chemical reaction networks that existed during comet formation. The presence of carbonyl sulfide also connects 3I/Atlas to broader questions about the distribution of complex organic chemistry throughout the galaxy. While OCS itself is not a biological molecule, its presence indicates chemical complexity that could serve as a precursor to more elaborate organic chemistry under appropriate conditions. The detection of OCS in an interstellar object also provides important calibration data for interpreting similar molecules in other astronomical contexts. The study of molecular abundance patterns in 3I/Atlas helps astronomers understand how to recognize and interpret chemical signatures of ancient stellar environments in other observations. The long-term preservation of carbonyl sulfide in 3I/Atlas demonstrates the remarkable stability of some molecular species in the extreme environment of interstellar space. This finding has implications for understanding how complex chemistry can survive and be transported between stellar systems over cosmic timescales. Fact 38. Hyperbolic escape velocity. The mathematics of 3I/Atlas's orbit are precise and unforgiving. Its hyperbolic trajectory has an eccentricity greater than 1, which mathematically proves that it's moving too fast to be gravitationally bound to the Sun. After its brief visit, it will escape our solar system with a velocity of about 58 kilometers per second, eventually reaching the outer Oort cloud in approximately 8,000 years. The orbital eccentricity of approximately 6.16 places 3I/Atlas in an extreme category of hyperbolic trajectories. For comparison, most long-period comets from the Oort cloud have eccentricities very close to 1.0, indicating parabolic or nearly parabolic orbits. The high eccentricity of 3I/Atlas reflects its enormous excess velocity relative to the Sun's escape velocity at any given distance. The escape velocity calculation demonstrates the fundamental energy balance governing 3I/Atlas's motion through our solar system. The total orbital energy, which includes both kinetic energy of motion and gravitational potential energy, remains positive throughout the encounter. This positive total energy is the mathematical signature that distinguishes bound orbits, negative total energy, from unbound escaping trajectories. The specific escape velocity of 58 kilometers per second represents the speed 3I/Atlas. Will have relative to the Sun when it reaches very large distances where the Sun's gravitational influence becomes negligible. This velocity is significantly higher than the escape velocities of any objects that formed within our solar system, providing definitive proof of the object's interstellar origin. The 8,000-year timeline for reaching the outer Oort cloud illustrates the vast scales involved in interstellar travel. Even at its enormous velocity, 3I/Atlas will require millennia to traverse the extended gravitational influence of our solar system. The Oort cloud, which extends to distances of roughly 100,000 astronomical units, represents the boundary between our solar system and interstellar space. The orbital mechanics calculations that determine these precise values require extraordinary mathematical precision. The gravitational influences of all major planets must be included in the calculations, along with relativistic corrections for the high velocities involved. Small errors in position measurements or computational precision can propagate into significant uncertainties in long-term trajectory predictions. The hyperbolic nature of the orbit also affects the observational geometry and timing for studying 3I/Atlas. Objects on hyperbolic trajectories spend relatively little time in the inner solar system, where they are bright enough for detailed observation. The compressed observational timeline reflects the fundamental physics of the escape trajectory. The comparison with other interstellar objects reveals the range of possible hyperbolic trajectories. Oumuamua had an eccentricity of about 1.2, indicating a much less extreme hyperbolic orbit than 3I/Atlas. 2I/Borisov showed an eccentricity of about 3.4, intermediate between the other two interstellar visitors. These differences reflect the diverse galactic environments and gravitational histories that shaped each object's trajectory. The mathematical certainty of the escape trajectory also means that 3I/Atlas represents a truly once-in-a-lifetime opportunity for scientific study. Unlike periodic comets that return regularly, or even long-period comets that might return after thousands of years, 3I/Atlas will disappear forever into interstellar space after its current passage. The precision of the orbital calculations also enables accurate predictions of 3I/Atlas's future encounters with other stellar systems. Computer simulations can follow the object's trajectory through the galaxy for millions of years into the future, potentially identifying future stellar encounters and gravitational perturbations that might alter its path. Fact 39. The galactic journey. During its billions of years wandering the galaxy, 3I/Atlas has likely traveled hundreds of thousands of light years, encountering gravitational influences from countless stars, stellar clusters, and massive molecular clouds. Each encounter would have slightly altered its trajectory and potentially its rotation, making its current path through our solar system the result of an incomprehensibly complex galactic pinball game. The scale of 3I/Atlas's galactic journey defies human comprehension. Over its estimated 11 billion year lifetime, traveling at speeds of tens of kilometers per second, the object has covered distances equivalent to multiple trips across the entire galaxy. The Milky Way itself is approximately 100,000 light-years in diameter, meaning that 3I/Atlas has potentially traveled a distance equivalent to several galactic diameters during its wandering. The gravitational encounters that shape this journey involve a complex hierarchy of astronomical objects with different masses and encounter probabilities. Close encounters with individual stars are relatively rare due to the vast distances between stars, but they can produce dramatic changes in trajectory when they occur. More frequent encounters with less massive objects or distant passages by massive objects contribute smaller but cumulative changes to the orbit. The stellar density variations throughout the galaxy create different encounter rates in different regions. The central bulge of the galaxy, with its high stellar densities and massive black hole, represents a particularly dynamic environment where gravitational encounters occur more frequently. The spiral arms, with their concentrations of young, massive stars and star-forming regions, create different types of gravitational perturbations. The molecular cloud encounters represent another category of gravitational influence that can significantly affect interstellar trajectories. Giant molecular clouds, with masses ranging from thousands to millions of solar masses, create extended gravitational fields that can deflect passing objects over large distances. The turbulent internal structure of these clouds can also create complex, time-varying gravitational fields. The cumulative effect of billions of years of such encounters creates what mathematicians call a chaotic dynamical system. Small initial differences in trajectory or encounter timing can lead to dramatically different long-term outcomes. This chaotic nature makes it virtually impossible to trace 3I/Atlas back to its specific stellar system of origin, despite our detailed knowledge of its current trajectory. The rotational evolution of 3I/Atlas during its galactic journey represents another complex dynamical problem. Gravitational encounters can alter not only the translational motion of an object, but also its rotational state. Close encounters with massive objects can induce tumbling motions, change rotation periods, or alter the orientation of the rotation axis through tidal torques. The preservation of 3I/Atlas's structural integrity throughout this long journey provides important constraints on the strength and cohesion of interstellar objects. The object must have survived countless gravitational stresses, thermal cycles, and potential impacts with smaller debris without fragmenting or losing substantial mass. The statistical mechanics of such a long galactic journey suggest that 3I/Atlas has likely sampled a representative range of galactic environments. Its trajectory has probably taken it through regions with different stellar densities, chemical compositions, radiation fields, and magnetic field strengths, exposing it to the full diversity of conditions present in our galaxy. The energy balance throughout this journey involves a complex interplay between gravitational potential energy and kinetic energy. While individual encounters can increase or decrease the object's velocity, the overall energy evolution depends on the statistical properties of the encounter population and the large-scale gravitational structure of the galaxy. The current trajectory of 3I/Atlas through our solar system represents just the latest chapter in this billion-year journey. The gravitational influence of our Sun and planets will add their own small contribution to the object's dynamical history, slightly altering its future path through the galaxy for the remaining eons of its existence. Fact 40. Temperature extremes. Throughout its interstellar journey, 3I/Atlas experienced temperatures just a few degrees above absolute zero. For billions of years, it existed in the cosmic deep freeze, with its volatile materials locked in a crystalline structure that preserved its ancient composition. Only now, as it approaches our Sun, are these primordial ices beginning to sublime and reveal their secrets. The temperature history of 3I/Atlas spans one of the most extreme ranges possible for any solid object. During its interstellar journey, far from any stellar heating, the comet's temperature was determined primarily by the cosmic microwave background radiation, which maintains a temperature of approximately 2.7 Kelvin throughout intergalactic space. This represents conditions only about 3 degrees above the absolute zero of temperature. The preservation effects of these extreme cold conditions are profound and far-reaching. At temperatures near absolute zero, molecular motion essentially ceases, chemical reactions stop, and volatile materials remain in their most stable solid forms. This cosmic refrigeration has acted as a perfect preservation system, maintaining the original chemical composition and isotopic ratios from the comet's formation billions of years ago. The crystalline structure of ices at these extreme temperatures differs significantly from the forms that exist at higher temperatures. Water ice, for example, can exist in multiple crystalline phases depending on temperature and pressure conditions. The particular ice phases present in 3I/Atlas preserve information about the pressure and temperature conditions during its formation and early evolution. The thermal evolution of 3I/Atlas as it approaches. Our Sun represents a dramatic transition from this ancient equilibrium. Solar heating increases exponentially as the comet moves inward, causing temperatures to rise from near absolute zero to potentially hundreds of degrees Kelvin at perihelion. This heating drives the sublimation processes that create the observable coma and reveal the comet's chemical composition. The rate of temperature increase depends on the comet's thermal properties, including its size, shape, rotation period, surface composition, and internal structure. Different materials absorb and conduct heat at different rates, creating complex temperature gradients within the nucleus that affect how and when different volatile materials begin to sublime. The thermal modeling of 3I/Atlas requires sophisticated calculations that account for the three-dimensional structure of the nucleus, the distribution of different materials, and the changing solar input as the comet moves along its orbit. These models help astronomers understand how the observed outgassing patterns relate to the underlying nuclear composition and structure. The preservation of volatile materials over billions of years at near absolute zero temperatures also has important implications for astrobiology and the distribution of organic molecules. Complex organic compounds that would be unstable at higher temperatures can remain intact in the interstellar deep freeze, potentially preserving information about the organic chemistry present in ancient stellar environments. The temperature contrast between interstellar space and the inner solar system also creates significant thermal stress within the nucleus as 3R/Atlas approaches the Sun. Different materials expand and contract at different rates as temperatures change, potentially creating fractures or structural changes that affect the comet's outgassing behavior. The measurement of temperature variations across the nucleus surface, if such measurements become possible, could provide detailed information about the thermal properties and composition variations within 3Y/Atlas. Different surface materials would warm at different rates and reach different equilibrium temperatures under solar heating. The long-term temperature history also affects the isotopic composition of the volatile materials preserved in 3I/Atlas. At extremely low temperatures, certain isotopic fractionation processes become ineffective, potentially preserving original isotopic ratios that reflect formation conditions rather than subsequent processing effects. Fact 41. The water mystery. The low water content of 3I/Atlas is puzzling because water ice is typically the most abundant volatile in comets. Several theories attempt to explain this anomaly. The comet might have formed in a region where water was scarce. It could have developed a protective crust that inhibits water sublimation, or it might have lost much of its water during its long interstellar journey through exposure to cosmic radiation. The water depletion observed in 3I/Atlas represents one of the most significant departures from normal cometary composition ever documented. In typical solar system comets, water ice comprises 70 to 90% of the volatile materials, with other species like CO2, Colorado, and various organic compounds making up the remainder. The 8:1 CO2 H2O ratio in 3I/Atlas completely inverts this normal pattern. The formation environment hypothesis suggests that 3I/Atlas originated in a protoplanetary disk region where water ice could not condense or was not abundant in the gas phase. This could occur if the comet formed interior to the water ice line of its parent star, in a region where temperatures were too high for water ice stability, but still cool enough for CO2 ice formation. Alternative stellar evolution scenarios could also explain the water depletion. If 3I/Atlas formed around a star that experienced unusual evolutionary phases or mass loss events, the chemical composition of the protoplanetary disk might have been altered in ways that reduced water abundance relative to other volatiles. The protective crust hypothesis proposes that 3I/Atlas does contain substantial water ice, but that this water is prevented from sublimating by a surface layer of non-volatile materials. However, this explanation faces challenges because it requires the crust to selectively inhibit water outgassing while allowing CO2 to escape freely, which is difficult to explain physically given that CO2 typically sublimates at lower temperatures than water. The cosmic ray processing hypothesis suggests that billions of years of exposure to high-energy cosmic rays could have gradually altered the surface chemistry of 3I/Atlas. Cosmic rays can break molecular bonds and drive chemical reactions that might convert water into other species or cause preferential loss of hydrogen, effectively reducing the water content over time. The isotopic signatures of the limited water detected in 3I/Atlas could provide crucial clues about which of these mechanisms is responsible for the apparent water depletion. Different formation environments and processing mechanisms would produce characteristic isotopic ratios that could be distinguished with sufficiently sensitive spectroscopic observations. The comparative analysis with other interstellar objects also provides context for understanding the water mystery. 2. I/Borisov showed more normal water abundances similar to solar system comets, suggesting that not all interstellar objects share the unusual composition of 3 Y/Atlas. This diversity supports the idea that interstellar objects sample a wide range of formation environments and evolutionary histories. The temporal evolution of water production rates as 3 Y/Atlas approaches perihelion could also help resolve the mystery. If water is present but inhibited by a protective crust, it might become more prominent at smaller solar distances where higher temperatures could breach the crust. Alternatively, if water is truly scarce in the nucleus, the CO2 dominance should persist throughout the comet's approach. The water depletion has important implications for understanding the thermal evolution and internal structure of 3 Y/Atlas. Water ice typically plays a crucial role in determining the mechanical properties and thermal conductivity of cometary nuclei. A nucleus dominated by CO2 ice might have significantly different physical properties that affect its response to solar heating. The search for water signatures also pushes the technical limits of current spectroscopic capabilities. Water has numerous absorption and emission features throughout the infrared spectrum, but detecting these features against the dominant CO2 signatures requires extremely high sensitivity and spectral resolution that challenges even the most advanced space-based instruments. Fact 42. Cyanide detection. Spectroscopic observations have detected cyanide, CN, in 3I/Atlas's coma, a molecule that forms when organic compounds are broken down by solar radiation. While cyanide sounds ominous, it's actually common in comets and provides important information about the organic chemistry that occurred in the comet's original stellar nursery billions of years ago. The detection of cyanide radicals in cometary comae represents a standard feature of cometary spectroscopy that has been observed in hundreds of solar system comets. The CN molecule produces characteristic violet emission bands in the visible spectrum that are among the most easily detected cometary features from ground-based telescopes. However, the context of CN detection in an interstellar object like 3 Y/Atlas provides unique insights into ancient organic chemistry. The formation of CN in cometary comae occurs through a complex photochemical process initiated by solar ultraviolet radiation. Parent molecules containing carbon-nitrogen bonds, such as hydrogen cyanide, HCN, or various organic compounds are broken apart by solar photons, releasing CN radicals that then fluoresce in sunlight. The abundance of CN in the coma thus provides indirect information about the abundance of organic parent molecules in the nucleus. The CN production process in 3 I/Atlas occurs under somewhat different conditions than those in solar system comets due to the unusual CO2-dominated environment. The photochemical networks that produce and destroy CN radicals depend on the overall chemical composition of the coma, and the extreme CO2/H2O ratio might affect the efficiency of CN production or its survival time in the coma. The detection of cyanide also provides important constraints on the organic chemistry present in the formation environment of 3 I/Atlas. Carbon-nitrogen compounds like HCN are key intermediates in the synthesis of more complex organic molecules, including amino acids and nucleotide bases that are essential for life. The presence of CN suggests that the chemical networks necessary for organic complexity were active in the comet's birthplace and Q. The abundance ratio of CN relative to other species like C2, C3, and OH provides diagnostic information about the types of organic compounds present in the nucleus. Different parent molecules produce characteristic ratios of daughter species when broken down by solar radiation, allowing astronomers to infer the composition of volatile materials that cannot be observed direct. The spatial distribution of CN emission in the Comet can also provide information about the outgassing patterns and nuclear activity of 3W/Atlas. Measurements of how CN brightness varies with distance from the nucleus reveal information about gas expansion velocities, photodissociation rates, and the distribution of active regions on the nuclear surface. The temporal evolution of CN production as 3I/Atlas continues to approach the Sun provides additional insights into how the organic chemistry responds to changing thermal conditions. Different organic parent molecules have different volatility and thermal stability, so the CN production rate might change in characteristic ways that reveal information about the molecular composition. The isotopic composition of the cyanide radicals, while extremely difficult to measure, could potentially provide information about the nucleosynthetic environment where the parent organic molecules formed. Different stellar types and evolutionary phases produce characteristic isotopic signatures in carbon and nitrogen that could be preserved in organic molecules for billions of years. The comparison of CN abundance in 3I/Atlas with that observed in solar system comets provides another perspective on the diversity of organic chemistry in different stellar environments. The CN other species ratios observed in 3I/Atlas will help astronomers understand how organic chemistry varies between different stellar systems and formation epochs. The detection of cyanide in an ancient interstellar object also contributes to our understanding of how organic molecules are distributed throughout the galaxy. The survival and preservation of carbon-nitrogen compounds over billions of years demonstrates the remarkable stability of certain organic species in the interstellar environment. Fact 43. The Gemini South observations. The Gemini South telescope in Chile has captured some of the most detailed images of 3W/Atlas's growing tail. These observations, conducted as part of an educational program that allowed students to participate remotely, show the comet's tail spanning about 1/120th of a degree across the sky, roughly equivalent to the width of a pinky finger held at arm's length. The Gemini South telescope represents one of the world's premier ground-based astronomical facilities, with its 8.1-meter primary mirror and advanced adaptive optics system providing exceptional image quality from its location high in the Chilean Andes. The telescope's southern hemisphere location provides optimal viewing geometry for 3W/Atlas during key portions of its approach trajectory. The educational component of these observations highlights the broader impact of the 3W/Atlas discovery on astronomy education and public engagement. The opportunity for students to participate in observations of an interstellar object provides a unique hands-on experience with professional-grade astronomical research that would have been impossible just a few years ago. The tail measurements obtained by Gemini South provide crucial data for understanding the dust and gas dynamics in 3W/Atlas's Comet. The 1/120th degree angular extent, while appearing small, corresponds to a substantial physical dimension when projected to the comet's distance. This tail length suggests active dust production and effective transport of material away from the nucleus by solar radiation pressure. The imaging techniques used by Gemini South for comet observations require specialized approaches to account for the object's motion across the sky. The telescope must track the comet's position precisely while maintaining stable image quality, often requiring exposure times and tracking rates that differ significantly from those used for stationary astronomical targets. The tail structure revealed in the Gemini images provides information about the outgassing patterns and nuclear rotation of 3I/8-less. Variations in tail brightness, curvature, or multiple tail components can indicate asymmetric outgassing, changes in gas production rates, or the influence of solar wind conditions on the Comet dynamics. The photometric analysis of the Gemini observations contributes to the brightness monitoring campaign that tracks 3Y/Atlas's activity evolution throughout its approach. The high-precision photometry possible with large ground-based telescopes provides important calibration data for comparing observations from different instruments and facilities. The adaptive optics capabilities of Gemini South allow correction for atmospheric turbulence effects that would otherwise blur the fine details of the comet's coma and tail structure. This technology enables ground-based telescopes to achieve image quality, approaching that of space-based observations, at least for brighter targets like 3Y/Atlas. The spectroscopic capabilities of Gemini South also contribute to the chemical analysis of 3I/Atlas through high-resolution observations that can detect and measure specific molecular emission lines. The large collecting area of the telescope enables detection of trace species that would be invisible to smaller instruments. The collaborative nature of the Gemini observations, involving both professional astronomers and educational institutions, demonstrates how major astronomical discoveries can be leveraged to inspire and train the next generation of scientists. The students participating in these observations are witnessing history in the making while learning advanced observational techniques. The data archiving and sharing protocols established for the Gemini observations ensure that the scientific value of these observations extends far beyond the immediate research teams. The images and spectra obtained will be available to the broader astronomical community for analysis and comparison with other datasets. Fact 44. Radiation processing. The unusual composition of 3I/Atlas might result from billions of years of processing by cosmic radiation and interstellar magnetic fields. This space weathering could have altered the surface chemistry, created new compounds, and modified the sublimation characteristics in ways that make the comet behave differently from pristine solar system objects. The concept of space weathering in interstellar objects involves a complex set of physical and chemical processes that operate over extremely long time scales. Unlike solar system objects, which experience space weathering primarily from solar wind particles and solar ultraviolet radiation, interstellar objects are exposed to the full spectrum of galactic cosmic rays, interstellar magnetic fields, and occasional encounters with dense interstellar clouds. Galactic cosmic rays consist of high-energy protons, alpha particles, and heavier atomic nuclei that travel at nearly the speed of light through interstellar space. When these particles strike the surface of an object like 3I/Atlas, they can penetrate several meters into the material, creating cascades of secondary particles and depositing enormous amounts of energy along their paths. The nuclear reactions triggered by cosmic ray bombardment can create new isotopic species and alter the chemical composition of surface materials. Spallation reactions can break apart heavy nuclei, while neutron capture processes can create unusual isotopic ratios that would not occur in normal stellar nucleosynthesis. Over billions of years, these processes could significantly alter the surface chemistry of 3Y/Atlas. The creation of new chemical compounds through radiation processing represents another important effect. High-energy particles can break molecular bonds and create reactive species that form new compounds not present in the original material. This could explain some of the unusual molecular signatures observed in 3I/Atlas's spectrum. The modification of sublimation characteristics through radiation processing could account for the unusual activity patterns observed in 3I/Atlas. Radiation damage can create amorphous structures in crystalline ices, potentially making them more volatile and prone to sublimation at lower temperatures than would be expected for pristine materials. The penetration depth of cosmic rays into cometary nuclei means that radiation processing effects are not limited to surface layers, but can affect material throughout the outer regions of the nucleus. This three-dimensional processing could create compositional gradients that evolve as different layers are exposed through sublimation. The magnetic field, interactions experienced during interstellar travel, could also contribute to the unusual properties of 3I/Atlas. Strong interstellar magnetic fields can induce electrical currents in conducting materials, potentially leading to heating, chemical reactions, or structural modifications over long time periods. The comparison with lunar samples and meteorites provides some terrestrial analogy for understanding cosmic ray processing effects. Moon rocks and certain meteorite classes show clear evidence of space weathering effects from cosmic ray bombardment, including modified surface compositions, altered crystal structures, and the production of unusual isotopic ratios. The quantification of radiation processing effects in 3R/Atlas requires sophisticated modeling that accounts for the flux and energy spectrum of galactic cosmic rays, the material properties of cometary ices, and the complex nuclear and chemical reactions that occur during particle bombardment. These models must operate over billion-year timescales, making them extremely challenging to validate experimentally. The implications of radiation processing extend beyond individual objects like 3I/Atlas to our broader understanding of interstellar chemistry and the evolution of small bodies in the galaxy. If radiation processing significantly alters the composition of interstellar objects, then the chemical signatures we observe might not accurately reflect their original formation conditions. The study of radiation processing in 3I/Atlas also provides important background information for planning future interstellar missions. Understanding how billions of years of cosmic ray exposure affect material properties is crucial for interpreting any samples that might be collected from interstellar objects, or for designing instruments that can distinguish between original and processed compositions, Fact 45. The Allen Hills connection. Some scientists compare 3I/Atlas to certain meteorites found in Antarctica's Allen Hills, which show evidence of extensive cosmic ray processing. Like these ancient space rocks, 3I/Atlas may carry isotopic signatures and chemical modifications that can only occur during extremely long exposure to the harsh conditions of interstellar space. The Allen Hills meteorite collection represents one of the most scientifically valuable repositories of extraterrestrial material available for laboratory study on Earth. These meteorites, collected from the pristine ice fields of Antarctica, include specimens that have experienced billion-year exposure times to cosmic radiation while traveling through space before falling to Earth. The cosmic ray exposure signatures preserved in Allen Hills meteorites provide a template for understanding what similar processing might produce in objects like 3I/Atlas. These meteorites show characteristic patterns of nuclear reaction products, including rare isotopes of noble gases, unusual ratios of cosmogenic nuclides, and modified mineral structures that serve as fingerprints of extended cosmic ray bombardment. The isotopic analysis techniques developed for studying Allen Hills meteorites could potentially be applied to 3I/Atlas if sufficiently sensitive remote sensing methods can detect the relevant isotopic signatures. Noble gas isotopes in particular provide excellent traces of cosmic ray processing history because they are chemically inert and preserve the signatures of nuclear reactions without subsequent modification. The comparison with Allen Hill's meteorites also provides constraints on the possible exposure age of 3:1/Atlas. The cosmic ray processing signatures observed in these meteorites correspond to exposure times ranging from millions to billions of years, with the most heavily processed specimens showing evidence of the longest space exposure times. The mineral alteration effects observed in Allen Hill's meteorites include the formation of shock-produced phases, the creation of amorphous materials from originally crystalline structures, and the development of unusual chemical zoning patterns that reflect the gradual accumulation of radiation damage over extended periods. The preservation of cosmic ray processing signatures in meteorites demonstrates that such effects can survive the violent processes of atmospheric entry and impact with Earth's surface. This suggests that similar signatures should be detectable in 3:Atlas through remote spectroscopic observations, provided that the sensitivity and resolution of available instruments are sufficient. The statistical analysis of cosmic ray effects in Allen Hill's meteorites reveals that different types of processing occur at different rates and accumulate different signatures over time. Some effects, like the production of specific isotopic ratios, occur rapidly and then saturate, while others continue to accumulate linearly over billion-year timescales. The thermal history analysis of Allen Hill's meteorites provides additional insights relevant to understanding 3:Atlas. These meteorites show evidence of having maintained extremely low temperatures during most of their space exposure, similar to the conditions experienced by interstellar objects during their journey through the galaxy. The organic chemistry preserved in some Allen Hill's meteorites also provides analogies for understanding the potential organic content of 3:Atlas. Despite billion-year exposure to cosmic radiation, some meteorites retain detectable organic compounds, suggesting that certain organic species can survive extended interstellar journeys. The microstructural analysis of Allen Hill's meteorites reveals the physical effects of extended cosmic ray bombardment, including the creation of microscopic damage tracks, the formation of exotic mineral phases, and the development of unusual textures that reflect the accumulation of radiation damage over geological timescales. The comparative analysis between Allen Hill's meteorites and 3:Atlas observations could provide unprecedented insights into the relationship between laboratory measurements of cosmic ray processing effects and the remote sensing signatures that can be detected in active interstellar objects. This comparison bridges the gap between detailed laboratory analysis and astronomical observation. Fact 46. Magnetic field interactions. As 3:Atlas passes through our solar system, it interacts with the Sun's magnetic field and solar wind in ways that create its characteristic coma and tail shape. The solar wind pressure shapes the extended envelope of gas and dust into the teardrop configuration we observe, with the tail always pointing away from the Sun, regardless of the comet's direction of motion. The interaction between 3:Atlas and the solar wind represents a complex magneto-hydrodynamic process that involves the collision between the comet's neutral gas coma and the stream of charged particles flowing from the Sun. As solar wind ions encounter neutral atoms and molecules in the comet's atmosphere, they can exchange electrons in a process called charge exchange, creating new ions and altering the dynamics of both the solar wind and the cometary material. The solar wind consists primarily of protons and electrons flowing radially outward from the Sun at speeds of several hundred kilometers per second. This plasma carries with it the Sun's magnetic field, creating the interplanetary magnetic field that permeates the entire solar system. When this magnetized plasma encounters the neutral gas cloud surrounding 3:Atlas, it creates a complex interaction region with multiple physical processes occurring simultaneously. The pressure exerted by the solar wind on the cometary atmosphere creates the characteristic teardrop or comet-like shape that gives these objects their name. The solar wind pressure is strongest on the sunward side of the coma, compressing the gas and dust in that region, while the anti-sunward side experiences reduced pressure, allowing material to stream away in the characteristic tail configuration. The magnetic field carried by the solar wind can also interact directly with any ionized material in 3I/Atlas's coma. When neutral atoms and molecules are ionized by solar ultraviolet radiation or charge exchange with solar wind particles, they become coupled to the magnetic field and can be accelerated to high velocities, contributing to the formation of ion tails that are distinct from dust tails. Fact 47. The rocket effect. You can't see. 3I/Atlas doesn't just fall past the sun, it also gently pushes itself around. As CO2 and dust stream off the nucleus, they act like countless tiny thrusters, creating non-gravitational accelerations that can subtly bend the trajectory and even tweak the spin state. That's why orbit solutions keep updating, outgassing physics layers on top of the clean hyperbolic math and solar wind interactions you've already covered. Think Comet as a leaky, rotating rocket. This ties directly to its escape geometry and the solar wind shaping of the coma and tail. Fact 48. Dust polarization. A free microscope. Light scattered by the coma's dust is polarized, and that polarization lets astronomers infer grain sizes, shapes, and how clumpy the dust stream is without ever touching the object. Coupled with high-end imaging, for example Gemini South's tail measurements, polarization mapping turns the coma into a live lab. CO2-driven activity should favor particular grain sizes and jet structures, so polarization angles and degrees are a fingerprint of Atlas's strange chemistry in action. Fact 49. The legacy, from one visitor to a playbook. Whether or not Juno pulls off a dramatic intercept, 3I/Atlas is already rewriting the checklist for future interstellar visitors. Start wide-field pre-covery hunts earlier, coordinate instruments fast in the fading window, and keep a ready-to-fly interceptor playbook. It cements the idea of interstellar comets as chemical time capsules and forces survey teams to plan for retrograde, high-speed targets with volatile rich comae. The next time a messenger drops by, we won't just watch, we'll be waiting. And that wraps up our journey through all 49 facts about 3I/Atlas. If you had fun diving into this cosmic mystery, make sure to hit the like button. It really helps push this video out to more curious minds. If you're new here, subscribe and turn on the notification bell so you never miss the next deep dive into the weird and wonderful universe. Got a favorite fact, or maybe a theory, about what secrets the next interstellar visitor might bring? Drop a comment below. I read them all and love hearing your thoughts. If you want to keep exploring, I've linked some of my other space breakdowns right here on screen. Click through and keep the journey going. And if you really want to support the channel, check out the description box for links to Patreon, merch, and socials, where we keep the conversation alive between uploads. Thanks for watching, and until next time, stay curious and keep looking